morning, good afternoon, or good night, depending on our time zone.
Meu Deus do céu.
Welcome to the session 5.
In Switzerland, there are no beds in their hospitals.
Hey, Fakher.
Hey, hi.
Hello, everybody. So please try to keep your microphones
There is a
muted,
hund in the
please.
Zoom meeting.
So, hi, everyone. It's good to see you all. Welcome to the session 5 of the 115 workshop, which was joined to the SCES webinar. So thank you, Philip, and the other organizers to allow us to join both events. I think they are interesting for both audience. So I hope you all are well in this difficult time, and I'm glad that you take the time to join us for this event. Okay, so I'm Pascoal Paliuza, I'm the chair for the session 5. And so I would like to tell you that the participants can ask questions after the talks using the raise hand feature in the Zoom. So in order to do that, you just click on participants, and you're gonna see a list of the participants on your right-hand side. And at the end of that list, you can see a small blue hand that you can click on to ask questions. You can also ask questions using the chat, write your questions in the chat, and the people in the Facebook can ask questions also using the chat, and we're gonna read the questions here. So thank you again. So our first speaker for this morning is Piers Coleman from Rutgers University, and his talk is gonna be about the 115 superconductors, window on a new world of quantum materials. So Piers, the Zoom floor is yours. Thank you all.
Thank you very much. Let me see if I can get my act together. Okay. Let me first share my screen. Good morning, everyone. Desktop 2, here we go. Okay, you're going to have to admit people. I'm not going to admit people to you'll have to take care of that. Okay, here we go. Well, good morning, everyone. Good afternoon or good evening, wherever you are in the world. It's a great pleasure to be invited to this online meeting. I should say that having a conference like this without being able to travel is in a way more stressful than having a face-to-face conference. You still have to keep your everyday life going. You still have to teach, do administrative things, and get your talk ready. So I'm getting the full experience here. So today, in my next 25 minutes, I wanted to share with you my perspective on the 115 materials. From a theorist perspective, you're always looking for clues for the wider story. And the 115s have been instrumental in forming our view of the behavior of quantum materials. And they really should be thought of in the context of a much wider group of materials. And the dramatic commonalities of this class of materials, such as their linear resistivities, despite the vastly different chemistry and structure, are a sign of new universalities of quantum materials. Here we have the 115 materials, the cuprates, the iron-based superconductors, and a new entry to this family, twisted bilayer graphene. So the discoveries in the 115s with their highly tunable properties have proven and continue to prove to be a vital window onto this key physics. And I wanted to remind you that the late David Pines regarded them as a Rosetta Stone for quantum materials. That's literally a quote of his from the year 2007 when he held a conference by this very title. Oh, why is that? I want to acknowledge my colleagues and collaborators, a whole cast of wonderful theorists, but also a whole group of experimentalists with whom I've discussed and collaborated with over the years. Why is it not giving me? Okay, so I've got a problem here. Let me go back a second. Okay, so here's the outline of my talk. I'm going to talk about first factors of 10 in TC and the historical ideas that were there before the discovery of the 115 materials. And I'm going to talk about the special role of these systems as exemplars of strange metallic behavior and quantum critical points. And I'm going to raise some of the key questions that are posed by these exciting materials. Then I'm going to talk about superconductivity and its connection with both magnetism and Kondo. Okay, and then I'm going to turn to open questions if I indeed get that far. Somehow, okay, maybe that's better. Okay, so the prehistory to the 115s, without doubt, a lot of the prehistory dates back to the discovery of the cuprate superconductors in 1987. And in that marvelous year, we became accustomed to a new range of superconductors with superconducting temperatures ranging from 10 Kelvin up to about 100 Kelvin. And many new ideas came out from this field. The phase diagram was much less rich than it is now, but we knew of the existence of a superconducting dome and an antiferromagnetic phase. And this then led to the rise of the notion of the quantum critical point. And here is a picture from the paper by Chakravarti, Halperin, and Nelson, as they started to consider the renormalization group associated with the quantum breakdown of the Néel state. And the vertical axis here is really 1/s. It's the coupling constant of the sigma model that they analyzed. And if you look at the references, the word quantum criticality, which was introduced around 1976 by both Hertz and Doniak in the context of the Kondo lattice, gradually started to grow with, for example, this marvelous paper by Scalapino et al. Discussing the possibility that at a spin density wave order parameter transition, you could get D-wave pairing. And there's a paper by Keimer where they discuss the magnetic phase and its finite correlation length, and there you find the word quantum criticality. And gradually, little by little, the question grew, could it be that beneath the superconducting dome, there might be a quantum critical point? So this then raised in the 1990s the question of, can antiferromagnetic intermetallics be driven superconducting by pressure? And this led to a whole group of experimentalists gearing up with new pressure cells and trying out antiferromagnets. Here is one that was well known for about 10 years. It's cerium-indium-3, which was discovered to be a 10 Kelvin antiferromagnet in the early 1980s, but it was also quite clearly a kind of Kondo system that had failed to go into a Fermi liquid. And so a whole bunch of experiments were done around this time. And here is the phase diagram of cerium-indium-3 with this tiny superconducting dome down at 0.2 Kelvin. And here are some of the other systems of interest that were studied at the time: cerium palladium-2 silicon-2 and cerium rhodium-2 silicon-2. And what these systems established was a definite link between quantum criticality and superconductivity. It suddenly became an experimental fact, not just a theoretical conjecture. And so enter the first member of the 115 family, cerium-indium-3, with this pathetically low superconducting transition temperature of 0.2 Kelvin. Now, just because a TC is low doesn't mean it's not interesting. And this led to lots of speculations. Well, what could we do to raise the temperature? And quantum chemists and materials designers of their era, working really as cowboys by the seat of their pants, such as Zach Fisk and also Gil Lonsrich and others, wondered whether cerium-indium-3 might be a starting point for new kinds of materials. And of course, what then happened was the discovery of cerium-rhodium-indium-5, which is literally cerium-indium-3 with another layer of rhodium-indium-2 spacing the layers. And of course, this system has a lower TC, T-Néel, but a much more substantial superconducting dome that forms beneath the quantum critical point. And this has become a poster child for our field. Shortly thereafter, it was discovered that there are the cobalt and iridium analogs with temperatures TC around 2 Kelvin. And then just 1 year later, plutonium, cobalt, gallium-5 was discovered by the group at Los Alamos with this factor of 10 increase in TC, which was literally understood as a result of having a band, the 5F band, which is broader and involves more valence fluctuations than the 4F band. A few more years later came neptunium, aluminum 2, palladium 5. And this is a wonderful example of material design. This compound was formed by accident in a palladium crucible. Aoki was trying to make something else, and lo and behold, he discovered this new 115, or should we say 125, superconductor. And we'll be coming back to that later. But the important point is that in 6 years, this field managed to raise TC by a factor of 100. And it's an amazing feat, and something that this field of physics should be immensely proud of. That raises the obvious question, the first of my talk: is there a common pairing mechanism amongst this family? And more important, even if there isn't, can TC be increased further? Could there, for example, be a transition metal analog of the 115s that would keep TC going on up higher? Well, of course, people have tried to make these materials, and so far, no success, and we don't understand why. So now I'd like to talk about the connection with strange metals and quantum criticality and the wider link. So coming back to this family of systems, okay, what are their commonalities? Well, one obvious commonality is the fact that they all exhibit around their quantum critical point, it seems, a linear resistivity. Perhaps we're less sure about the twisted bilayer graphene, but we do know that as we dealt with phosphorus, the ion-based superconductors can be driven through something that looks like a quantum critical point with a linear resistivity. And here is cerium cobalt indium 5 on the left. Let's have a closer look at these examples. Here are the cuprate superconductors, and they not only exhibit this linear resistivity at low temperatures, but they also transform into what is called a bad metal at high temperatures, where the mean free path is comparable with the lattice spacing. Okay. Here is cerium cobalt indium 5, which shows anisotropy and a more perfect linear resistivity along the C-axis than along the AB plane, where it transitions into a T to the 3/2 at low temperatures. This work by Tanata et al. Examined the possibility of deviations from a Wiedemann-Franz law and seemed to find it for transport in the C direction. Okay. And so nowadays, this phenomena has been given the name Planckian dissipation. Why? Well, first of all, it's a cool name. But second of all, it seems that the transport time in these systems is literally, scattering time is literally the Planck time. It has no other variable in it other than the temperature and some constants of order 1. Okay. And this contrasts with a Landau Fermi liquid where the scattering rate grows like a T squared. Another aspect of these systems, which is not commonly given much thought, is the fact that they exhibit a strongly temperature-dependent Hall constant with a cotangent of the Hall angle, which is basically 1 over the Hall angle, which grows not as T, as you might expect from linear and T scattering rate, but as T squared. And in this pioneering work by Ong et al., they were able to show that even if they doped YbCO with zinc, this scattering rate just moved up constantly, independently of temperature, the shift, showing that this looks like an independent scattering rate. Okay, and later on, the same phenomena, perhaps in an even more beautiful form, was seen in cerium cobalt indium 5 around its this is basically measurements at around 4 Tesla, I guess. And so this is very interesting because commonly in a Drude picture, we think of the Hall angle as being given by omega c tau. But in this case, you need to have a Hall scattering time, and that Hall scattering time seems to behave like a Fermi liquid. So this is very, very puzzling, and it's a completely unsolved problem at the current time. But we can make some questions about it. First of all, is there a common origin for this behavior? For example, is it associated with Mott or partial Mott localization quantum critical points? We don't know yet whether this behavior is seen, for example, in the bilayer graphene systems. Okay. And secondly, is the appearance of 2 relaxation times the sign of momentum space anisotropy, or is it a sign of some kind of electron fractionalization? And for those of you who have their feet squarely planted in the world of conservative condensed matter physics and have their doubts about the word fractionalization, let me point out to you something very important. The Hall conductivity in these systems is a product of two different transport times. And yet the Hall conductivity is determined by scattering at the same momentum, at the same point on the Fermi surface. And so this multiplicative behavior of the scattering times, which is empirically deduced, really suggests that we should associate two relaxation times with each point on the Fermi surface. And that's surely a strong qualitative argument for the idea of fractalization being an element of these systems. And it was a point that was made very strongly by Phil Anderson, who, it must be said, associated this scattering rate with the spin-ons and then puzzled us all by wondering why spin-ons would be involved in the Hall constant. Okay, let's go on. What about the change in the Fermi surface volume? Cerium rhodium indium 5 is a poster child for this phenomenon, and we've seen many times at this meeting the wonderful work of Shishido et al. In 2005. I wanted to point out, oh, and by the way, we also saw this beautiful work by Shim and Denninger, a nice example of how experiment and theory can work together. And they were able to show that over the range of 1000 Kelvin downwards, this part was done using DMFT, it seems very likely that the change in the Fermi surface volume is indeed 1 unit of electron charge. And this is strongly reminiscent of Oshikawa's theorem. This is the topologically based theorem from 2000, where Oshikawa deduced that the spins must rigorously contribute to the Fermi surface volume if you have a Fermi liquid. Okay, so moving right ahead, what about other parallels? Well, we've heard in recent times of the beautiful work by the Sherbrooke group, where they show, at least they argue, based on their Hall analyses, that the small Fermi surfaces seen in de Haas van Alphen at high fields transition into a large Fermi surface through a change in the Hall constant. And this is perhaps signs that this phenomena of small to large Fermi surface transition may be much more general, maybe a general feature of a quantum critical point near a strange metal transition. Okay, and so I wanted to pose one more question, one question that had arisen at this meeting. What happens to charge fluctuations when the Fermi surface jumps? And charge fluctuations can, of course, be seen through the transverse optical conductivity, but in principle, they can also be probed by Mossbauer measurements if you can only get them to work. And we saw one new advance in that respect at this meeting, which is the E/T scaling measured in YRS near its quantum critical point, the work of Fakher et al. This is a beautiful piece of work, and it raises the question whether similar measurements might be done in the 115's. Okay, now let's turn in my remaining time to superconductivity. We know a lot about the superconductivity in the 115's. Okay, whatever comes next. There's many indications of nodal D-wave pairing from thermal transport, from NMR. Here is the NMR relaxation rate of many of these systems, showing a T-cubed relaxation rate developing, a sure sign of nodal behavior. Interestingly enough, T-linear, the sign of Fermi liquid behavior, is not so common, and you see this upturn here, characteristic of non-Fermi liquid physics in most of these systems. Thermal transport in a magnetic field shows this nodal anisotropy, and STM quasiparticle interference of both the Seamus-Davis group and the Princeton group shows that there seems to be nodal excitations with a D wave. Let me come back to that. A D wave form factor. Okay, so far these seem to be like miniature high temperature superconductors. But there are some important differences that I want to bring to your attention, okay? And one beautiful example of this is Neptunium, the Neptunium-115 material discovered by Dai Aoki in 2007. And if there's one thing I'd like to push for is more experiments on this marvelous material. This system shows a nice linear resistivity before it goes superconducting, okay? And what's perhaps most remarkable of all is this. It's a Curie paramagnet. It shows Curie-Weiss behavior down to TC. And it's also very anisotropic, showing that local moment physics is preeminent in this system. So what does that tell us? Well, first of all, it's a very remarkable system, but it tells us that spins are around right down to TC, okay? It goes from Curie to paramagnet to superconductor. Lest you doubt that, let's look at some of the data. Well, first of all, the specific heat capacity shows an anomaly with a huge entropy of condensation. This entropy of condensation is the entropy associated with this local moment, okay? And similar behavior can also be seen in cerium cobalt indium 5, complicated by the interplay of crystal field effects. You see Curie-Weiss, and then some kind of coherence or crystal field effect, and then an even stronger Curie-Weiss at low temperatures. And in a similar way, we know there's a large amount of spin entropy left over, because we also see a large jump in the specific heat capacity, about a third log 2 spin entropy, okay? You might think that those spins are still hanging around in the superconducting state, but they're not, because the night shift shows that the 1/T behavior seen at high temperatures disappears at low temperatures. So the local moments disappear into the condensate. And we know even more about this from the upper critical fields. Here is the upper critical field of the Neptunium system, and it shows this remarkable jump in magnetization at the upper critical field, which is a first order transition. And the jump is about 0.2 Bohr magtons. Similarly, in the 115's at cerium cobalt indium 5, this jump is even bigger. It's 0.3 Bohr magtons. This is this magnetic moment begins to be manifested inside the Q phase. But either way, it signals a release of the local moment from the condensate at HC2 and raises a fascinating perspective that we've got a transition from local moments at high fields and high temperatures to a singlet condensate at the phase transition. And this is then a paradox. And it suggests that the spins must be contributing to the condensate Hilbert space. And so this led us in 2008 to propose the idea of composite pairs. And I just want to end talking a little bit about the concept of composite pairs, particularly because Laura Green introduced this day before yesterday in a lovely talk. And so what is the concept of composite pairs? Well, this was first introduced by Schrieffer, Balatsky, and Abrahams in the context of odd frequency pairing, but it doesn't have to be odd frequency pairing. And a composite pair is literally the notion that to add electrons to the condensate, you have to add them as a pair, but flip a spin at the same time. So the order parameter is not just an electron pair, but actually a spin flip times an electron pair. Now that's not so crazy because we already know that an F electron is basically a spin flip times an electron. But to make this work, you need 2 electrons in 2 different orbitals. And that's why we propose in 2008, and Rebecca Flint will talk more about this evening, the idea that there may be a 2-channel physics behind the engine of superconductivity in the 115's. And how can that be? Well, these F1 configurations or F5 configurations, depending on what you're talking about, fluctuate their charge not only to a predominant singlet state, for example, from F3 to from F1 to F0, but they can also go to the doubly occupied state. And if the channel for charge fluctuation has a different symmetry, then what happens is you end up with a Kondo model with 2 different screening channels. One is probably weaker than the other, so it's not perfectly symmetric, but that doesn't matter because they've got different symmetries and they can, in the lattice, stop competing with one another by forming a composite superconductor. Okay, and this is one of the things that comes behind the hood of that theory, the notion that as the local moments fractionalize, their fractionalization is manifested by a hybridization in 2 symmetry channels. One of them is a hybridization and the other is a pairing. You can't tell which one is which because there's a gauge symmetry which relates the 2. But an electron comes in and becomes an F electron, and then it Andreev scatters through the Kondo effect out into the conduction C. Okay. So Rebecca will tell you more about that this evening, but one of the things that I find very interesting is the possibility, as yet unproven, that this kind of mechanism might be important for these fascinating new planar tunneling measurements of the group of Laura Green. And what they've seen is that even though we know that the coherence temperature of the system is about 40 or 50 Kelvin, and that we have Kondo effect turning on in a coherent way at higher temperatures, we seem to have a low energy scale, which is Zeeman split by the time you get to about 5 or 6 Tesla. And so this suggests that there may be two components to the Kondo effect, and this second channel Kondo effect may be responsible for the Zeeman splitting of this planar tunneling signal and might be a contender for the pairing in this system. This doesn't mean the end of super exchange driving pairing, because this mechanism doesn't compete but actually works together with such a mechanism. I'm out of time and you should have stopped me. So here are my open questions. Okay, first of all, is there any way to make transition metal 115s? If you could do it, and I know it doesn't make sense, people are going to say, well, the spin orbit coupling isn't so strong in the transition metal system, so why would you imagine that? There's no strong Hund's coupling, or maybe there is. But nevertheless, it's like making an airplane. If it flies, you worry about why it flies afterwards. So secondly, the strange metal and the quantum critical point. As I mentioned to you, magnetotransport suggests the same underlying mechanism in the cuprates and the 115s. 2 relaxation times. These suggest fractionalization on the Fermi surface. Okay, and we need conceptually based theoretical tools. We saw this beautiful work of collaboration between Ji-Hoon Shim's group and Jonathan Denninger's group, where they were able to use, in conjunction, high quality ARPA's data with an NCA solver for DMFT to bring things together and show us that we do have one whole electron being absorbed into the Fermi surface as we go down in temperature, albeit very gradually. And for me, this exemplifies the importance of developing new theoretical methods and concepts, because the methods that they use are now almost 40 years old. They were, in fact, I should know them well, developed by Kuromoto and myself in my thesis. They are the NCA method. And so this is work that was done in 1984, and the method now becomes an engineering tool in the year 2020. So the message here is that the tools we develop now using our bare bones, simplistic models in analytic theoretical physics become the engineering tools of our science in 10 years or 20 years or 40 years time. And so this is a big bit for trying to push the frontier of conceptually based analytic theoretical condensed matter physics to help us in the future. Secondly, what happens to the charge mode at the small to large Fermi surface transition? Can it be detected in 115s in transverse or longitude, I should say in transverse optical modes or longitudinal probes? Superconductivity, the spins survive till TC, at least they do in the Neptunium system, and then they quench. And this suggests composite pairing. Can the excitations into the F2 state be detected? We've seen amazing advances in photo emission, but the inverse photo emission has been left behind. And there is scope here for both new analyses of STM data and inverse photo emission, perhaps looking at what's happening when we excite, for example, from the F1 to the F2 state. Okay, and that's the end of my talk. Thank you.
Okay, so I would like to ask the audience to unmute themselves so we can give Piers a very nice round of applause. Okay, thank you very much, Piers. So the presentation is now open for questions, comments.
The first comment is we cannot unmute. So you need to allow people to.
They should be able to unmute themselves.
Okay, well.
No, okay.
No, we cannot, says Chi Miao C.
Okay, so I'll figure out how to do that. Okay, so I have a question from Jim Allen. Please, Jim. So let's unmute him. Unmute Simiao.
Raise your hands if you want to ask a question.
Oh, I'm,
Please.
oh yeah.
Hey, Jim.
Hi, yeah, just a lovely talk. It's really fun to listen to the big picture laid out with ideas to cause us to think and questions to be answered. I enjoyed it a lot. I wondered whether the fractionalization that you have in mind would be peculiar only to the superconducting state, or whether you have in mind that it's also present in the normal state. And in that case, then we might think that good RPES could try to look for signatures of that, like we try to look for in the Luttinger liquid, for example.
Jim, thank you for your comments. Well, you know, in fact, if you look at Denninger's data, which is your data, I guess, you see that even though the characteristic size of U in these systems is like 2 volts, aka 20,000 Kelvin, which means that at 1,000 Kelvin, you're basically behaving as a Kondo system, that you're seeing the large Fermi surface grow. And so from that point of view, you've got a system which is dominated by local moments, which is nevertheless showing a large Fermi surface developing. So from that perspective, those spins are starting to fractionalize as they come down in low temperatures. And the large Fermi surface is an example, we know in some sense, that when you flip a spin, you create a pair of heavy fermions. And so is that not already fractalization of the local moments? And so perhaps it's been under our nose all this time. We should be reinterpreting the large Fermi surface in a Kondo lattice as the fractalization of the local moment. After all, that moment could come from a nuclear spin. We know it comes from F electrons, of course, but the physics doesn't know anything about the fact it came from F electrons. It's a local moment that is fractionalized. And so I think it's very helpful to think about the Kondo system as being a fractionalization of the spins, and then the phase transitions will be a modification of that fractionalization.
Yeah, I do remember that you were fond of pointing out that if one uses just the Kondo model without the charge degrees of freedom of the Anderson model, nonetheless, you do find the large Fermi surface. I have remembered that over the years and pondered how I might think about it. Thank you.
Thank you, Jim. So next question by Jimmy Yao, please.
Thank you. So Piers, nice talk. I want to follow up on the thread of a normal state versus superconducting state that Jim just sort of created. So in the CeIrIn 115 systems, we've spent the past couple of days discussing the phase diagram, and it seems like there's a very strong empirical connection between quantum criticality and sort of heavy Fermi high TC superconductivity. I wonder how much information, so maybe there's a question for both for you and experimentalists, how much information do we have to try to connect this Neptunium 125 material into this overall phase diagram, whether, first of all, whether that's possible, and secondly, if so, how to place it in the overall phase diagram with the placement of potential quantum critical points in the overall picture.
Yeah, so, you know, it's a little bit like the plutonium system. In its own family, there's no immediate sign of a magnetic ordering transition. Nevertheless, that doesn't necessarily mean that it's outside this class. It could just be that we've got, well, it could just be that it's just over the horizon. And it's true that when you go to the indium-based plutonium systems, you do see the magnetic phase transitions again. So it looks like we're quite close to a magnetic phase transition. It's just possible that there might be elements of an underlying strange metal phase beneath the superconducting dome that were just prior to the formation of the antiferromagnet. So we might be in that region of the phase diagram where the localization occurs without magnetic order, and perhaps that then produces a superconducting dome on top of it. I don't know.
I mean, but as a field, it would be fantastic if we can try to create an axis which connects this
Yes.
4.5 Kelvin TC with the CeIrIn5.
One key thing there is encouraging our experimentalists to push for the ability to make new samples.
Mm-hmm. Thank you, Piers.
Thank you, Chimiao. Please do not touch the screen. If you touch the screen, you can add something to the screen, because
I see that someone has been doing graffiti on my beautiful screen.
Someone is trying to collaborate with you. I'm very sorry about that. So please.
No, that's okay. That's fine. I think it's funny.
Because this Zoom is configured for a class, so sometimes the student can do that. So I'm sorry. Okay, so next question is, let's see, it is Silk. Do you have a question? See if you can unmute yourself. Okay, that's great.
Yes, hi, Piers. Thanks for the great talk. I have a question to your sort of two-channel Kondo interpretation of the superconductivity. Would that have any consequences for the resistivity then also being maybe non-Fermi liquid like for other reasons, like namely for two-channel Kondo reasons?
Yes, so that raises the interesting question of whether there is some deep universality between non-Fermi liquid driven by two-channel physics and non-Fermi liquid behavior driven by partial localization. And we simply don't know the answer to that at the moment, Zilka. None of us can really calculate resistivity in a convincing way. However, let me just speculate that if indeed we're seeing the transition from a fractionalized spin in the form of a large Fermi surface to a small Fermi surface where the spin is behaving more like a local moment, then that transition may be universal. And the soft charge modes associated with it, whatever they are, may be responsible for this universal linear resistivity. So there may be a universality there, which is separate from the detailed mechanism by which the non-Fermi liquid behavior comes about.
Okay, thanks.
You're welcome. Great to see you.
Next question by Henry Allal, please.
Hello.
Salut, Henri.
Salut. Do you hear me?
Bien.
Yeah.
Très bien.
Okay. I am a little bit amazed by this local moment which disappears when it becomes superconducting. I don't know very well these 115 systems, etc. But at least this effect is a little bit strange. The TC is 4.2 K. So I assume that one can kill superconductivity. Do you restore the local moment when you do that? Is there an experiment?
This is a point, actually, Dai will probably return to that more this evening, although I realize that's not going to be accessible for you from Paris. But the point is, and it went by fast, is that when you look at the upper critical field, you see this jump in the magnetization, and it's about 0.2 of a Bohr magton. So their interpretation is that the spin is coming back into the magnetic world. So it does seem to be there just on purely thermodynamic grounds. You literally see a jump in the magnetization. So this is the, years ago, people thought that spins were bad for superconductivity. This is the exact opposite. This is a system which uses the spins to make the superconductivity.
Conductivity, yeah. So in the superconducting state, they disappear.
They have entangled with the electrons to make new kinds of pairs. That's what we think is going on.
But is there a way to be sure that they disappear? Because you have diamagnetism in the superconducting
Yes,
state.
so that's where the night shift is so important, and Nick will tell us more about that. You can measure the night shift in the normal state. You can see the 1/T behavior, and then it goes away when it goes superconducting. So even though you've got diamagnetism, you can probe the local susceptibility and show there are no spins left.
Yeah, you would see it also in T1 somewhere.
Yeah, well, 1/T1 goes to a T-cube behavior as it goes superconducting. So they're definitely gone, and the entropy shows they've gone too.
Okay.
So they depart as they go superconducting.
This is a very original behavior. Okay, thank you very much.
You. Salut.
Salut.
Marco Civelli has raised his hand.
So next question by Marcelo Civelli, please.
Hi, hello, Piers. Thanks a lot for your nice. Nice to see you, even so far.
Yeah.
I have a very silly question, actually, about this composite superconductivity. Would you see any trace of it in the pairing function, if one could see the pairing function? Because that's not trivial.
Absolutely. So, and of course, you know about this from your own work in dynamical mean field theory, where you see poles developing in the Andreev scattering. And so this is a rather similar thing, and we tried to do it and didn't succeed in doing this at Rutgers. But presumably, if you take a two-channel Kondo solver with two different channels and embed it into a DMFT calculation, you should be able to see these superconducting Andreev scattering events with poles in them developing.
Okay. That's what I wanted to know.
Yeah.
Thank you.
Well, you're welcome. Great to see you. Looking forward to pizza together sometime.
Oh yes, will be wonderful. Thank you. Ciao.
See you.
Okay, let's see. Any further question or comment? I don't see anyone.
Oh, Roman Moshkovich said that plutonium, cobalt, gallium-5 has a Curie-Weiss susceptibility down to TC.
Okay.
And Roman, good comment, but your colleagues in Karlsruhe disagree with you. And this is something that needs to be resolved, whether there is or is not a Curie-Weiss susceptibility down to TC in plutonium, cobalt, gallium-5, because one set of measurements says yes, and another set of measurements says no. It's a difficult measurement, I gather, because you've got to embed the sample in some stuff that protects it, and that makes it difficult to measure the specific, the magnetic susceptibility.
Okay, Piers, can I ask a question? Pascal?
Yes.
Yeah, sure.
Oops, I'm going to turn on the video because it's not showing. So thermal conductivity in cerium cobaltinium 5 also has a jump at TC, right? So the first order phase transition is reflected in electronic degrees of freedom. So how do we separate the first order phase transition, just like Professor Henry said, that there is a diamagnetism in superconducting state, and so the jump in magnetization, which is reflected in thermal conductivity as well, there is a jump.
Yeah, that's a good point.
It's more of an electronic.
So you're saying your valid point is, could that jump in magnetization be an orbital, some kind of orbital effect, and it's not really the spins coming back at all? And I don't have an honest answer to you, Roman, but presumably one can do some thermodynamic analysis, and maybe one could do something with the NMR at those high fields. I don't know. Interesting question. Or NQR. But I don't. It's a good point.
I wonder if your approach will explain the jump in thermal conductivity.
Well, first of all, I don't know, but if there are significant changes in the Fermi surface morphology, underlying Fermi surface morphology, then the quasi-particle behavior will change rather suddenly as well. But so I would think that's very natural. But I really would like someone to check again that Curie-Weiss susceptibility of plutonium, cobalt, gallium-5. I think it's important to double check.
Fair enough. Thank you.
Okay.
Any further questions or comments? Yes, Joe Thompson, please. Joe?
Sorry, Piers, just to follow up on your last response, we have checked maybe 5 or 6 different samples of plutonium, cobalt, gallium-5. Some show the Curie-Weiss behavior, some show it to a less extent, but irrespective of what ITU finds, there is always at least some remnant of a Curie-Weiss behavior, even in their what looks like their samples.
I see. I'd love to see that data. That's very interesting. Maybe you should write up that data.
Well, maybe, yeah.
Okay, any further questions or comments? Okay, so if not, now I think everybody can unmute the mics. So let's do that and give Piers a very nice round of applause.
Thank you.
Okay, so let's move for the next talk. So the next talk will be given by Fakher Assaad from the University of Wurzburg, Germany. And the title of his talk is Kondo nano-structures and lattice quantum Monte Carlo studies.
So, good afternoon. Everything seems to be working. That's amazing. So thank you very much for the invitation, and especially since I don't really work on the 115, and what we do is more numerical, of course, and what we do is to try to develop, we use Monte Carlo methods to investigate Kondo systems from the single impurity to the lattice. And Piers was putting emphasis on tools, how important it is to develop tools. Well, this Monte Carlo, of course, is limited, you'll see, is limited in what we can do, but it has the big advantage of being exact, right? In the sense that it goes beyond the MFT and it takes local fluctuations as well as spatial fluctuations exactly. So the outline of the talk is the following. I will first, let me get rid of this, right? I will first introduce very, very quickly what the method is, this Fermi Monte Carlo, and then I'll pick up two sort of toy models which allow us to look at rather interesting things in the realm of heavy fermions, and that's the role of magnetic frustration, and also the second point, which will be here, which is I put in the laser pointer, some very simple models where we can have some Kondo breakdown transition in nanostructures, and then I'll conclude. So for the funding, all these labels here are funding for positions, for postdoc and PhD position. I especially like to emphasize this new cluster of excellence between Dresden and Wurzburg, and that's just great to be able to collaborate with people from Dresden. And all this list below, we do numerics, so we need CPU time, and we also need some money to do some program development, some packages development. So thanks to all these institutions that help us to fund this. Before going on, if ever I'm able to move, I'm not able to. Uh-oh. I cannot move my thing. I think it's here it is. Perfect. So these are my collaborators. These are the people in Wurzburg, right, who are all working on quantum Monte Carlo methods. I especially like to point out Bimla Danu, right, who has done a lot of the calculations on the Kondo system. Toshiro Sato, who also has done some of the simulations for the frustrated systems, and also Marcin Rakowski, who is also working on the Kondo. And this work has also been done in collaboration with other people, Matthias Wojta, who is here, right, Frédéric Millat, and a long-term collaborator, Tarun from UCSD. So let me start. If ever, this is hard to, I really don't know how to make it move. This is it, perfect. So what type of Monte Carlo do we do? I'm trying to get rid of something here, and I'll get rid of it, and then I'll move on. Sorry. Here it is. That's perfect. Okay. So what is the Monte Carlo we do? We basically work in thermal equilibrium, and the biggest central quantity is the partition function of a given model, a Kondo lattice model, for example. And what we do is we decompose this partition function over a sum of fields. These X fields are space and time dependent. And for each of these configurations of fields, we can attach an action. This is an action of a one-body problem in an external field. And if I give you a field configuration, this is, since it's a one-body problem, I can solve this in polynomial time. And the idea is then to do the integration over all these fields by Monte Carlo sampling. Good. So what does this work? In principle, yes, and of course also no, because it's quantum mechanics. So if S is complex, this is not going to be something which is positive definite, and we will not be able to use this as a weight factor. And so this essentially, we start with a problem which is exponentially difficult, And if this sign problem comes in, then we don't gain anything. The problem remains exponential and computationally exponential, and so we cannot advance. Now, there's a set of models where we can show that this action here is real. And in this case, this is a weight, and I can do the Monte Carlo samplings rather efficiently. And there we can solve problems, fermion problems coupled to spins. I'll show you some very general examples in polynomial time. So that's pretty exciting. One thing which is also exciting in this approach is that there has been a big improvement or in the class of interesting, so that's up to you to decide if it's interesting or not, but in class of interesting negative sign-free models we can solve. So this is a list of references which have concentrated on this problem. And it turns out to be a rather mathematical problem. The question you will have to ask yourself is, if I give you a set of n skew-symmetric matrices, then if I take this trace over Majorana's, what are the conditions on these skew-symmetric matrices so that this trace is bigger or equal to 0? That's the question you have to ask. So that's all I'm going to say about the Monte Carlo, and I'm going to show you one type of class of models which we can solve, which is a pretty general model of spins coupled to fermions, right? Which is essentially what we want for heavy fermions. So let me start with the spins. So the spin degrees of freedom live on a graph, which I label by I and j. And to be able to do the simulations in polynomial time, we have just one conditions for the spin system. The only condition is that this j perp of ij has to be smaller than 0, right? If it's smaller than 0, we can always simulate this problem. Essentially, this is actually very general, since it includes, for example, Z2 spin liquid. I mean, the balanced Fisher and Gervin model can be simulated if you're able to simulate Hamiltonians of these forms. Then we have a fermion part, and the fermion part lives on another graph, which I label by x and y. And this matrix T, this hopping matrix T, so let me take one step back. You have to be able to separate this graph into A and B sublattices, and this hopping can only connect sites between the A and B sublattices. So, for example, there's no chemical potential, which you cannot put in the chemical potential. That would give you a sign problem. And essentially, what it tells you is that your system will be nested in one way or another. And there's the Hubbard U, which you can add on this graph. So how do we couple these two things? And the way we can couple it without introducing the sign problem is through a sort of modified Kondo coupling. So JK for us is positive. And this is, if I take away this -1 to the x, then this is a generic Kondo coupling between the localized spins and the fermions. I need this -1 to the x to be able to get rid of the sign problem. That's how it turns out. So these are everything I want to tell you today is based on this rather general model and different instances of this general model. So to continue, if you want to check our results, we have developed a package. It's a quantum Monte Carlo package. It's called ALF, for Algorithm for Lattice Fermions. It's not easy to use. I'm the first to say this. We have a very good documentation for this, and you can download it, read it, and check our results. And it's actually also great fun to develop those packages. So I won't take much more about this. So let me now start with physics and on magnetic frustration. So this work was done with Toshihiro and Taru. Good. So let's start with classics. I think that you all know this, the competition between RKKY and Kondo screening, then as a function of a Kondo coupling J that will lead to quantum phase transition between antiferromagnets and Kondos. I mean, I'm thinking here in terms of a half-filled problem. The question we would like to ask here is what happens if we put in another axis to this diagram, which is phase, which is frustration. And there a lot of things can happen. For example, there could be Kondo breakdown transitions and Kondo phases which violate the Luttinger volume. So Piers was talking about this before. To be able to violate the Luttinger volume, if you have to bypass Hoshikawa's topological topological Luttinger volume theorem, you have to try to get some type of fractionalization into play. So these are FL star phases where essentially the spin degrees of freedom are a Z2 spin liquid with topological degeneracy, and this can decouple from the conduction electron and actually violate the Luttinger volume. So we have some simulations where we have tried to do this, and what I will show you later on are very sort of baby examples of FL star phases where spin 1 chains decouple from conduction electrons. And then another possibility, if you enhance this frustration axis, is partial Kondo screening. What I mean is that there is a symmetry breaking, a spatial symmetry breaking, and essentially what happens is that the Kondo screening becomes sort of position dependent so as to alleviate frustration. I'd like to show you that this works in a very specific example. The specific example we have is a Kondo lattice on a honeycomb. So let's forget about this frustration effect for the moment. So this will, it's a half-filled, so Dirac fermions coupled to spins, right, to lattice of spins. And so without any frustration, essentially we have the phase diagram here is an antiferromagnetic insulator, and here a Kondo insulating phase. The frustration we put in is in the Z direction, and these are these triangular lines. So a honeycomb lattice, builds two interpenetrating triangular lattices, and what we have here is on this red triangle lattice and on this blue triangle lattice, it's an Ising model on the triangle lattice. So this is a classical frustrated system. So let's see what happens to this phase diagram as a function of this frustration. Of course, if the frustration is small, and essentially everything will flop into the XY plane, and we will have here an XY antiferromagnet. So this breaks the U1 spin symmetry of the system, and then there's a U1 or XY transition to a Kondo insulator. The Kondo insulator has the full symmetry of the problem, namely that's a U1 spin symmetry. The interesting part of this phase diagram, if you go to higher frustrations, then you really generate new phases, and these are what we call Z partial Kondo screen phases. If we look at this phase, we can classify it in terms of symmetry. It's a Kondo screen phase because it has the same symmetry as the Kondo phase. It has a U1 spin symmetry, but it has broken translation symmetry in the sense that Kondo screening becomes site dependent. There is a very simple way of understanding this in this specific model, this phase, and you can go to, for example, to the t=0 limit, where the A and B sublattices, so that would be the A and that would be the B sublattice, for example, they decouple. So we can just think of terms of one of these triangular lattices. And when t=0, you have a conservation law, namely the total Z component of the spin, so the Z component of the total spin, here, for example, on these two sites, is essentially a good quantum number. Right? So the Hamiltonian commutes with this operator. Now, because the Kondo scale is positive, we expect the ground state to have a total SZ of total Z of 0. So we can work on each site. We can work in a reduced Hilbert space. There are two degrees of freedom. One, like I'll call a super spin up, a super spin down, which is up down or down up. Now, in this space, essentially, this model reduces to a Ising model on a triangle lattice in a transverse field, right? So the magnitude of the transverse field is the Kondo coupling. And this is a model which has been solved where we know what the ground state is. This is a work of Piers Coleman, for example. And there are, depending on chemistry, there are two possible scenarios. One is a spin up, spin down, or super spin up, super spin down. And then this is an X direction, or one spin up with a large magnitude and two spins down with a small magnitude. And essentially what we see in this partial Kondo screen phase is this structure for one sublattice. So that would be, for example, up, large up, and then down, down, right? So it's a three sublattice ordering. And when you put in the T perturbatively, then you lock the other lattice. If this is up, this is down, and then this is then up, up with a small. So this gives you a realization. I think it's one of the first realizations where you can really couple, you can really look at frustration effects in Kondo systems and see that you get some new phases which have been proposed also experimentally, these partial Kondo screen phases. Good. So let me go on. The second thing I'd like to talk about is also rather new, is the possibility of having very clean Kondo breakdown transition in nanostructures where we can progress in our understanding of these type of phase transitions. This is actually work which has been motivated by very nice experiments in Sander Otte's group in Delft, and they consider cobalt atoms on a copper 100 surface, but importantly, there is a decoupling layer of copper nitride. So we can look at start with a single impurity case to see that everything is okay. This is cobalt has a spin 3/2. There is a single ion anisotropy, which essentially splits the 3/2 to high energies, and there is a low energy doublet, right? So in the STM, you will see this threshold here is exactly this energy. And at low temperature, you see a very nice Kondo resonance, meaning essentially that the STM sort of, you tunnel through the cobalt d orbital. So that we call it, I'll refer to this as co-tunneling. So it's very easy to model this theoretically. I have my conduction electrons here, so that would be the copper 100 surface. I have my spin here, this is a spin 1/2, which takes into account this twofold degenerate level. This is the spin of the conduction electron, and I can add a magnetic field. The scales, we can read them off. The Kondo scale is the width here of the 0.2 electron volt. That's important, so that means that we can overcome it with a magnetic field which is not too big. To reproduce this results, the co-tunneling, well, we just can calculate the spectral functions of these d tilde fermion operators, which are nothing but if you start with a periodic Anderson model, these are the localized, the F electron and D electrons in the Anderson model. You go through a Schrieffer-Wolff transformation, and you will obtain this this is a assisted, you tunnel by flipping, you tunnel from the copper to the tip by flipping a spin essentially. So we can calculate this with the Monte Carlo, the spectral functions, and we have a very nice Kondo resonance. So nice for the setup. What is remarkable is in this experiment, in my opinion, is that they can build chains, right? So they can build 1, 2, 3 up till now 9. That's what they published up to now. And so the generalization of the model is actually very nice. We still have the conduction electrons. This is the coupling to the Kondo coupling to the conduction electrons. And what is also important is that they have an exchange between a Heisenberg term between the cobalt atoms. And you can see this very nicely by looking at, so this is, for example, the Kondo resonance for a single impurity in a magnetic field. So you see the splitting. This is for 2 impurities. So you see that there is the STM, you see that there is a gap here, and this gap essentially reflects this energy scaling, this energy scale, the Heisenberg term between the chain, if you want, of spin 1/2 degrees of freedom, and you can overcome it with a magnetic field, and you will have here a magnetic field induced Kondo resonance. And you can do this for 2, 3, 4 up to 9 cobalt atoms, etc. And this model, which is very simple, can reproduce the data. So this is, I'm not going to go through this. It's just too much data for this short talk. But you can see that if I take the 3, just 3 atoms, this is the zero bias DIDV. And so you see that I have a resonance here. This corresponds to this, right? There is a resonance maybe here, which corresponds to this, etc. And so if you go through this, then you see that this experiment is extremely well described by a very simple toy model, and we can make essentially a one-to-one comparison. This is the motivation, right? This is the motivation, and it allows you to ask you a different question, which maybe at one point experimentally realized. And then we would like to look now at an infinite chain of spin 1/2 degrees of freedom. So this is the infinite chain of spin 1/2 degrees of freedom. It's Kondo coupled to conduction electrons. And to make things analytically tractable, I mean, that's what Tarun and Matthias tell me, analytically tractable, we will take Dirac fermions in the sense that it's still a Lorentz invariant system. So we put in a pi flux here for the specialist to get our Dirac fermion. We can do some analysis of this model, and first take the case JK equals 0. If I take JK equals 0, my spin 1/2 degree of freedom has a 1/RdK, meaning that the scaling dimension of the S is 1/2. The scaling dimension of fermions for a Dirac fermion is basically d divided by 2. So if you do a power counting for this term, you will see that it is irrelevant, meaning that the decoupled fixed point is stable. Of course, you have another limit, which is the limit where we go to strong coupling. In the limit of strong coupling, so this is a JK, just put JK to infinity, then you will have a set of direct products of F electrons or D electrons and conduction electrons, and essentially this direct product state will decouple from the conduction electron. We can do for this model, we can do, or Tarun and Matthias can do an epsilon expansion, a renormalization group analysis based on an epsilon expansion around the upper critical dimension, which is 2.5 in this case. And what you find is a renormalization group flow, which is actually very reminiscent of the one you have for a single impurity in a semi-metal. We have a decoupled point where things are, where you basically the spin chain and the Dirac firms are decoupled. We have a strong coupling fixed point where it's Kondo screened, and we have a Kondo breakdown critical point. So there's a Kondo breakdown phase, that's what I like to call it, where things decouple, Kondo breakdown critical point, and a Kondo screen phase. So that's what you would get before doing simulations. And the question is really what happens in the simulation. So see, here's some data which was taken by Bimla. And so it's a very nice model because we know so much about the Heisenberg chain. I mean, for example, the Heisenberg chain, we know that because of SU2 spin symmetry, this enforces the spin-spin correlations to decay exactly like 1/r with an antiferromagnetic prefactor. So we know if in the decoupled phase, we know exactly what to expect. These are the spin-spin correlations for different lattice sizes. And this line here shows the 1/r decay, which you have at the decoupled point, JK equals 0. You go up to JK equals 1.5. So this is pretty big because the antiferromagnetic J in the chain is 1. So this is 1.5 times bigger. And remarkably, you see exactly the 1/r decay. If you go to bigger JK, so there's a deviation. And if you go to very large JK, then essentially the spin-spin correlation along the chain sort of inherits the decay of the spin-spin correlations in the bulk, in the Dirac metal. And for a Dirac metal, the spin-spin correlations decay is 1/r to the 4. So this is more or less consistent with the 1/r to the 4. What you can also do is to do neutron scattering. So you would do neutron scattering just on the chain. Of course, we can do that numerically for one chain. I think neutron scattering would be a bit hard, but we can do that. This is the well-known 2-spin-on continuum for the case where JK equals 0. We see exactly the same thing, or very similar, right? At least within the limitation of this. This is something which is technically pretty tricky. We have to do a Vic rotation, which is hard, I will admit. But we have very, very much the same 2-spin-on continuum. If you go to JK equals 3, then you see that you're losing weight here, meaning that the spin-ons bind, right, to form essentially a spin degree of freedom. So these are a lot of data which signals the phase transition. The last data which was taken by Bima is much more suggestive, and this is the co-tunneling. So you essentially put as I said before, you put an STM tip on top of one of the cobalt atoms and see if you can tunnel through the copper. If you are, and you look at the zero bias at omega equals 0, the zero bias conductance, if you are in the Kondo breakdown phase, then you would expect nothing, and that's exactly what we see up to 1.5, and then beyond 1.5, at least at 2, we were starting to see sign of the heavy fermion. You start that this picks up, and we can very well understand when JK goes to infinity, then this signature has to go down to 0 because we generate these Kondo, very strongly bound Kondo singlet. So this is an example, a very simple and clean model where you can have a Kondo breakdown transition. I think there's a lot to do, understand this criticality, understand how to characterize this phase, what measures do we need to take to characterize this phase, etc. In a certain sense, this was a warm-up. This was a warm-up exercise, since if we want to take back a step to the experiments. The experiments, at least for this copper 100 surface, is a spin chain on a metal. So the next the calculations we are doing now is exactly the same, you know, the spin chain, Kondo coupled to, now this is a metal. The metal we have, because of the constraints we have, has nesting. So it has a nested Fermi surface. We cannot get rid of this. And we can start working on this model. We already have some results. But essentially, if you start thinking about the model, it's much more complicated, because if you start from the decoupled fixed point and you integrate out, you put, just put jk equals 0, and then you try to see what happens at small jk's, you can integrate out the fermions, and you will essentially, like in the Helmholtz type way of doing things, and you argue that the Kondo coupling is marginally relevant. So for the moment, we don't really have a very good understanding of what will happen, but our preliminary results are maybe showing that Kondo breakdown will not happen in this system, but we still have to work on it. So I'm at the end of my talk. I hope that I have persuaded you that this auxiliary field Monte Carlo is a powerful and most importantly, approximation-free tool to study many interesting things in Kondo lattice models. I repeat it, we design our models to make them sign-free. Sometimes we can be close to experiments, sometimes we can't. And the two examples I've talked to you, that I've mentioned, are Kondo breakdown transition to nanostructures, which, as I said, are very clean and can be really studied very well. And also problems of how to, models where frustration and Kondo interplay and compete and generate new phases of matter. And so with this, I would like to thank you, and I'm happy to take questions. Yeah.
Okay, let's give Fakher a nice round of applause, please. Okay, so the presentation is now open for questions. So Jim Allen, please.
Yeah, I wondered whether some things that you could do with this method might give insight into the idea that Piers was presenting, that maybe we should think of Kondo as a kind of fractionalization, which would be a rather new way to think about it. And I have always wondered over the years if there was something I could do, something that could be measured, that would somehow turn it from a different way of thinking into something that you could somehow prove experimentally as showing that it was the right way to think about it. Thank you.
So maybe Piers, you can help me answer that question. So normally, I'll start like this. Normally, when we have fractionalization, like in the spin chain, and we would like to detect it numerically or even experimentally, we look at, for the spin chain, we just look at the neutron scattering. If you have a spin, you fractionalize it, then you have two objects, and if you flip one spin, then you will have a continuum of these two objects. So you would like to, Piers, tell me if I'm going in the wrong direction.
I agree with that. I guess the question would be, do you see a large Fermi surface?
Yes, we do.
So then you've got the 2kF coming from the spins and from the electrons, right?
We see that, but this is not, so you can, this is something you also get in a large N approximation. This is, so you claim that this is fractionalization, right?
Well, large N is kind of a pre-fractionalization, it's kind of a fractionalization ansatz in some sense.
Right, I can agree with that. But there are, so if you have, let me put the answer this way. If you have fractionalization, you necessarily have some type of constraint in a gauge field which emerges, no? Something like that. Would you agree with that?
Yeah, absolutely. But I mean, if you flip a spin in the large Fermi surface phase, you should see a continuum which has the larger value of 2kF, right? So in the case of your honeycomb system, you presumably should go from a system with no Fermi surface to a system with a Fermi surface, at least along the chain, no?
So along the chain, there is exactly this. Along the chain, we have a, well, this is decoupled. So this would be, but this is, so we do have, along the chain, we have a Fermi surface with a 2kF and no 2kF here, correct?
Okay, so that I would say is a kind of fractionalization.
Sorry?
It's a funny thing because in some sense, both sides are fractionalized.
Yes, exactly. So this is it's a, so it's fractionalized here in the sense that we have spin-ons, right?
Mm-hmm.
Right.
And on the right-hand side, you have heavy fermions, but they come from the spin dosa.
Right. So that will be for you a fractionalization also. But how do I pick it up to get back to Jim's question? So what do I measure? What would I so you say I would measure the Fermi surface here 2 kF or bigger, so kF plus 1 actually, right?
You see, it's hard for the experimentalists because you know you've got a local moment there because you put it into your theory, right? Whereas the experimentalist, of course, there's still the real electron sitting down there that makes the local moment, and how to separate out the fact that you had an F electron there originally,
right,
and the fact that from the claim that the spin is fractionalizing. And I think it's very difficult when it fractionalizes as an electron. Right. It's when it fractionalizes something crazy that you start to get surprised, and then you can probably test in various ways.
I mean, the thing that always bothered me over the years is that if we get at this with photo emission, we're pretty confident that we really did extract an F electron from the system.
That's true. That's true. And of course, but at low energies, that photon coming in is in some sense, if you think about it in the Schrieffer-Wolff language, you have to do a Schrieffer-Wolff transformation on the current operator that the photon connects to. And that will now be re-expressed in terms of a kind of co-tunneling operator. So from that point of view, you can write down the photon coupling. Someone should do this as an exercise in the Kondo lattice.
Okay.
Yeah.
Okay, so perhaps we should move for the next question. So Andrew, have a question, please?
Yes, Fakher, this is Andriy Nevedomsky. Thanks for a very nice talk. May I ask a question to the first part?
Yes.
Where you talked about the lattice. So actually this picture would do well. When you write down the Hamiltonian, my question would be if you kill the JZ, the interaction between the spins. So if I look at the horizontal axis in your plot, what is it that makes the spins order into XY antiferromagnet? Is it the sort of the coupling to the 2kF Friedel oscillations of conduction electrons and the sort of RKKY type effect?
Here they would couple through an RKKY.
Right. So this reminds me of a work by Ivar Martin and Christian Battista. What they studied is a Kondo lattice model, a toy problem on a triangular lattice in their case, where what was happening is that the conduction electrons had, the Fermi surface was nested. I mean, in your case, this is charge neutrality, right? So you have 2 points. In their case, they had a nested Fermi surface. And as a result, it's that nesting instability that led to the ordering of spins, even if you didn't have an explicit spin-spin coupling. Are you saying that something similar happens here, even though the density of states vanishes linearly at the Dirac points?
So the density of states vanishes linearly at the Dirac point. I agree, and essentially the answer to your question, we always find a magnetically ordered state. The magnetism here is a mass term, right? Is a mass term for the Diracs, and it will open up a gap. Right?
And it happens spontaneously without you having any staggered moment.
Along all this line, even if you do a mean field approximation along all this line, you will have a gap, essentially a single particle gap, which is proportional to JK, and we can look at that also numerically, right? So there is a mass gap. So this here you have a mass gap because antiferromagnetism is a mass term for the Diracs, and here of course you have a mass gap because of the Kondo spin.
I see.
And so
I see.
that's flowed from one to that. That's the answer. Right.
Thanks.
Okay, so next question by Yashar Komijani. Yashar, please.
Hello, thank you for a very nice talk. I have 2 questions for these 2 figures. First, the Kondo breakdown figure. So my question is that would you imagine that this has a sharp rise and then a long tail on the right side. So would you imagine that this sharpens as you go to larger system size? The spectral function.
So this is the spectral function at omega equals 0. Will it sharpen and go to bigger system sizes? That's a good question. I don't think so. It should stay finite, right? I mean, it's essentially like I think it should stay finite, Yasha, but I cannot.
At the Kondo screen size, you expect it to be finite.
Yes, in the Kondo screen size, I do expect it to be finite. I mean, I'm taking the intuition from the single impurity Kondo, right? For example, that will be fine.
I see. And then, am I right that the symmetries on the left and right side is the same? They both have all the symmetries of the problem.
There's no symmetry breaking.
So can you sorry?
There's no symmetry breaking. Correct.
And then can you interpret then the peak, the sharp rise, as a charge mode in the system, there is a critical charge mode you can tunnel in or out without costing any energy.
So you want to interpret this as a charge mode?
Yes. Yes.
It's interesting. We should measure. So your claim is that the charge correlations should become critical at the transition, something like that.
Yes, that's what we find using large N or group of chemiosiphines using EDMFT. Yes.
So it's a bit. So we would have to. We could very well. We haven't analyzed the criticality of this model for the moment. That's rather new, but in principle, it's possible to look at the charge fluctuations just on top of the chain essentially, and see if there's some type of criticality we can pick up there. Now, how to relate the single particle. This is a single particle quantity, Yasha, right? How to relate the single particle quantity to critical charge fluctuations. I would have to think about that. I don't have an answer right away.
I see. Thank you. Can I ask another question about the lower figure? So you showed that in the strong coupling limit, the frustration axis can be mapped to a transverse field Ising model on a honeycomb lattice. So is there an easy way to think how the adding tunneling perturbatively would affect that universality class, the Ising universality class of this system?
Basically adding T. I mean, if you put T equals 0, you have two independent.
So without T, I suppose all these lines are Ising universality classes.
Yeah. Of course, it's an Ising universality class. I agree. So the 3D Ising universality class. So you're talking the transition, right? It would be a 3D Ising universality class between in the Ising transverse Ising field model. Now you're asking me the question: what happens to the T? The T, what it does is it couples. So these are two triangle lattices. You know, one is here, right? And the other. So I'm sorry, one is here like this, and the other one is here like that. And the T is actually couples these two Ising fields, right? So that so then I would have to understand if I double the degrees of freedom, instead of a one scalar field, I have two scalar fields, and I couple them, if that will change the universality class. That would be the way to.
Like
okay, so
coupled
that
Ising system.
Yes. Coupling two times. You're coupling. Right.
Perfect. Thank you so much. Thank you.
You're welcome.
Okay, so next we have a question from Philip Roney. Philip?
Yeah, hi, thanks for the talk. I guess I'm curious, you did the frustrated Kondo lattice at half filling, right. And I'm wondering if you can say anything about the relative stability of the partially Kondo screen phase if you could move away from half filling and get a metallic state. Is there anything you can say about that?
Well, for the moment, no, because we haven't done the calculation. I'm sorry, so I don't. This is speculation. As soon as we move away from half filling, we have a sign problem. So I mean, this is so it all then depends on energy scales. You know, if I can, and there are some cases where you can't assume that the energy scale where, as Yasha was saying, this is Ising criticality, so it should survive somehow at finite temperatures, right? So if it survives to high enough temperature so that I can, you know, reach this temperature with the method before being confronted to a very severe sign problem, then I could answer the question. But we haven't tried, right? So it all depends on scales. So the takeaway message is that it is possible to dope, but it's we're limited in the energy scales we can reach, and then you have to be sure that the energy scales are big enough, large enough to be able to reach them. So sorry, I don't have an answer to your question.
All right, thanks.
Okay, last question from Benedict, please.
Hi, yes, can you hear me?
Yeah. Yes, I can hear you.
Okay, thank you. First of all, thanks for the nice talk. Also, as someone who does variation in Monte Carlo, I was going actually in the same direction when what happens if you go away from the half-filled case. You just said that it's a question of energy scales. So that means you immediately run into this problem that at some lower temperature, you will end up with a severe sign problem. Is that correct?
Yes. Yes, you can show. Yeah. Yes.
Go ahead.
Yes, you can show that the cost of your simulation scales exponentially with inverse temperature.
So I was wondering, there are some approaches where people combined also the auxiliary field approach with variation wave functions, where you essentially get rid of the sign problem. Did you think in that direction, or? I mean, then there is some bias, of course, in your results, but based on what you've done so far in the half-filled case, it might be possible to guess or to have an educated guess for variational wave function that might be suitable.
That's a very good question. Doping it's not easy to I think it's not so easy to get intuition of the doped phase based on what happens at half filling. I mean,
yeah, that's true.
You look at it's a big step. You ask for intuition at half filling so that I think is rather hard. So the answer is I mean, this is phase transition. You know, doping is a metal insulator phase transition. So
yes, yeah, and you could also end up with something superconducting, for example.
You could end up with something else. It could be a first order phase transition, for example, and you have no clue of what happens when you dope. So I think getting intuition from there from the half field is hard. The other question is variational. Yes, I think variational is a way to go, right? It's of course there's some type of bias. There are many methods like PEPs or IPEPs, which are essentially are very good for the dope phase, right? For dope phase, they come with their limitations, but that I think if you want to go to the doping, then maybe you're better off with a good intuition or with PEPs or IPEPs. That would be my take.
Okay, thank you.
Okay, so now we should move for the next talk. So let's thank the speaker again. Thank you. So next talk will be given by Cris Adriano from University of Campinas, Brazil. And the title of her talk is What Can We Learn from the 218? Cris, please.
Hello, everybody. We'll share screen. Okay. Can you hear me?
Yes, we can.
Okay, thanks. It's weird when no one answers because. First of all, I would like to thank the organizers for the invitation to participate of this wonderful workshop and SCES webinar. So I hope everybody is doing great, and it is very nice to meet you all, even virtually. And I think the most important thing is that we all are healthy and we should stay with family and friends. And that's just to thank everybody to be here, as we are all friends, like trying to understand the beautiful physics of the heavy fermions. So today I will talk about what we learned from the CeIrIn5 as we don't talk much about them, but I will try to show you work that has been done since, I guess, Pascual was at Los Alamos, so over those many years already in our group. So I'm having that problem. Okay, so that are some of the collaborators at this work. So basically a group from Campinas, my collaborators from the APS, Professor Lim from Nesse, my collaborators for Los Alamos, from Sirius, Brazilian Light Source, and from CBPF. And so why this? Okay, so the outline is, I will try to give you a short overview of the CeIrIn 218 and then show you most of our results from past, present, and then future perspectives, showing mainly cadmium doping, CeIrIn 218, and our results on neutral magnetic diffraction and cadmium and iridium simultaneously effects and crystal field studies and ARPA's results. So just to start, as everybody might already remember, that CeIrIn 218 belongs to the broader family of cerium indium 3, the 115's, and then the 218's. And the 218's increase, we see an increase of dimensionality that's supposed to be toward more 3D-like electronic structure, but it's not what really ARPA's showed us. And that was expected because we have a second cerium 3 block on the block structure. So then what changed with the dimensionality? So the little overview, cerium 2 cobalt indium 8 superconductor at TC of 0.4 Kelvin. Cerium 2 rhodium indium 8 is an antiferromagnetic at 2.8 Kelvin. And cerium 2 iridium indium 8 is spin glass at 0.6 Kelvin. The rhodium member becomes superconductor if we apply pressure and also if we dope with iridium. So that's the phase diagram for cerium 2, rhodium 1 - X, iridium X, indium 8 for ambient pressure. We can see coexistence between superconductivity and antiferromagnetism. But if we compare with the very famous 115 phase diagram, we can see that for the 218s, we see a smaller range of coexistence and also lower values of TCs when we compare when the 115s. So continuing on the overview, that's the phase diagram when we apply pressure. So we see two superconductor states with distinct pressure evolutions and also some disorder states at the region side of the phase diagram. So that all those phase diagrams are also similar to what we could see for the 115s. So cerium 2 rhodium indium 8 was studied and had its magnetic structure determined by Weibull, and he found a magnetic structure with propagation vector half-half 0 and moment direction 52 degrees away from the AB plane, and effective magnetic moment of 0.55 Bohr magnetons. So that's the cerium 2 rhodium indium 8 magnetic structure, and that's comparing with all the other members of the family. So we see that cerium 3 has propagation vector half-half-half, so it kind of becomes the 218 and 115 keep some of that behavior. So all of them has the magnetic structure with propagation vector half-half something, and 115 is incommensurate, and the 218 is commensurate magnetic structure with half-half 0. So then I will show you cadmium dope in cerium 218, what happened with CNEL. This is just to show that we doped the rhodium member, the iridium member, and if we put all the results together in a phase diagram of now temperature as a function of doping, including here radion half, iridium half. We see that cadmium is increasing now temperature for 3 members of the series. So cadmium is favoring the anti-ferromagnetism for 2 and 8s as well as for the 115. So here I just included the data from FEM work from cadmium doping 115s. Of course, here I just put now temperature behavior. So it's then we conclude that cadmium is acting as an electronic tuning agent for both series. And then if we see what happened when we dope on the behavior of Tmax, calling so that the resistivity as a function of temperature for serum 2 radium unionate, and so that's the coherence associated with the maximum. So that's what I'm calling Tmax. So that those are resistivity as a function for both radium and iridium as a function of temperature for dopings. And then if we plot Tmax as a function, okay, host asked it to start my video. It's there. So can you see me now? And so we have Tmax as a function of X, and so this is an unusual behavior of the maximum temperature from the resistivity data that is not expected in the Doniak-like scenario. So it means that from here we already know that crystal fields might be important, will be important for cadmium doped 218. So a while ago, we determined the magnetic structure for cadmium doped CeIrIn 2 radium indionate. At that time, we used X-ray resonant magnetic diffraction and neutral magnetic diffraction. So I'm not giving you details on the techniques. If you want, you can ask me later. But then we fit the model, and what we found for cadmium doped sample is that we increase the effective moment as expected for doping with cadmium, but the moment direction is going toward to the AB plane. We studied that same cadmium compounds, a function of pressure. So those are resistivity measurements, and what if we put like both Tmax and now temperature as a function of pressure, we could see that Tmax has a minimum on the curve around 9.5 Kelvin and 1.4 gigapascal, and Tnel remains nearly constant, but no superconductivity was found to 3.6 gigapascal. So we perform neutral magnetic diffraction at NCNR. What we found, like those are intensity as a function of temperature and model. So we see that as a function of pressure, compound remain with same propagation vector, now temperature does not change. And the effective magnetic moment is decreasing. So that summarize what we saw at the neutral magnetic diffraction experiment. So as pressure is increasing, moment is decreasing, and the moment direction is going toward the AB plane. So what we could see is that initial decrease of Tmax roughly coincides with the pressure range for which the magnetic moments are rotating to the AB plane. So applied pressure is rotating the order moments, which should be associated with change on the crystal field anisotropy. So, and then we continue our work. So we did experiments with both iridium and cadmium doping. So that's a beautiful phase diagram in which Dennis compiled all beautiful data. So we could see Tmax increasing, Sommerfeld, the coefficient that increased a little bit as a function of iridium. We did magnetic structure experiments. We determined the magnetic structure for all of those 3 compounds, and those are simulations of using experimental data, and to give us the moment direction and everything else. So, and that table summarizes our results so far. And what we could see is that basically both cadmium and iridium doping are making the moment direction going toward the AB plane. So that's a nice result. And then continue here. What happened is that Denise, it's a PhD student from Pascual, she did crystal field analysis using this model here that I don't have time at all to talk about, but that a while ago already our group did nice calculations showing that changes on the crystal field parameters can explain behavior of the oriented moments. So what Denise did, she took paramagnetic susceptibility fit constrained by the moment direction from the neutral magnetic diffraction experiments. So she did, and also that model does not consider Kondo effect. So that she did first for the rhodium member doped with cadmium. That's the crystal field parameters, and that's the scheme. And what we could see here, however, is that the cadmium is like lowering the whole and the levels to lower energies. And I don't need to explain you again beautiful results from Professor Sabrin group showing the alpha behavior of the crystal fields of the ground state wave function as a function of rhodium and iridium. So we just use that to have an idea and conclude that cadmium appears to be decreasing the crystal field splitting, leading to the variation of occupation of excited levels, so possibly increasing the XY anisotropy. And then final is that CeIrIn2 rhodium indium and with 6% of cadmium is unlikely to become a superconductor even at higher temperatures because the moment is going toward to the AB plane. So we are having flatter 4F distributions. So we also did the same kind of crystal field analysis on the other members, like with iridium and cadmium doped, and we have beautiful results. And I will ask you to see the contributed talk of Denise that is at the web page of the event, because I won't be able to explain you all, and she did it beautifully, but I will try just to give you the highlights. So those are all the crystal field splits that she found. And we can see that as alpha of the 5 halves is not changing so much, it suggests that we have a constant contribution of the 3 halves state at the ground state functions, because alpha is not changing much. However, we still have an evolution of the magnetic structure toward the AB plane for both cadmium and iridium doping. So that means that all the excited states have to be considered to account for the physical properties. So the overall effect of cadmium is for both like a rhodium member and rhodium half, iridium half, is that cadmium is lowering the excited states for both members, and that increases the planar anisotropy of the J5 halves, and then that favors the antiferromagnetic ground state. And also effects of iridium, So iridium increased hybridization, as we could see from Tmax and gamma coefficient. Also, we have the screening of the magnetic moment. So excited states become more easily populated, what in fact could contribute to increase also the anisotropy, and at the end it favors antiferromagnetic ground states. So what then changed with dimensionality? So first, all the excited states have to be considered to account for physical properties. Cadmium appears to lower the excited levels. Iridium enhances the hybridization. And all of this favors in the 218 scenario, antiferromagnetic ground state. So now I jump for ARPA's measurements on CeIrIn2 rhodoninium-8, a little bit late on time. So that's my collaborator Fanny Rodolakis from the APS in Aragon, and that's my student Kevin. They were responsible for helping me analyzing data that we took some time ago already. So I first start showing you the band structure of this compound as a function of temperature. So we're gonna tell me, well, nothing is changing. Yeah, perhaps it's very hard to see change. That's why I'm trying to show you here. So the measurements were, I just realized that the low energy measurements were done at the already closed Synchron Radiation Center at Wisconsin, and the on-resonance measurements were done on the Synchron Light Source in Brazil that was already closed. So I found it funny. But anyway, for the low energy measurements, that was our best resolution case. It's about 15 million electron volts resolution, and that will be important to show the next results. But that is how we get data from ARPAs. We have a band structure that is an energy as a function of momentum, and for those experiments, we rotate the sample in front of the beam, and so then we access the other values of the moment along the Brillouin zone. So that's the temperature dependence of the band structure, pointing here that is in low energy. So I'm comparing 330K with 300. What we do, we could, as those maps are very difficult to take results, so we plot the momentum distribution curves that are the indices. So we can make this for all energies we want. We can like integrate a little bit to see better what's going on. So we did that for all temperatures we had. And then what I will show you are those in red that are the indices at AF, like at the Fermi energy. And I plot them together. So this is what's happening for one side. So gamma M or ZA side of the Brillouin zone. And this is what is going on as a function of temperature for other direction. Sorry, said side is direction. So here we could see that's very messy, bands are collapsing, and it's very hard to see what's going on. So it's very hard to follow because we don't have enough resolution to separate all of the bands on this side. And on that other direction of the Brillouin zone, we see one big peak that seems not moving and another peak that moves more linearly. So on gamma X, bands move linearly, and at gamma M, it's kind of messy. So that finally then the Fermi reconstructed Fermi surface of CeIrIn2 rhodoninium-8 at low energy, at low temperature, high temperature, yay. So things are changing, but not too much. We see complicated topology of the Fermi surface. At that energy, we are near Z point, so that is even worse, it changed less. So we could identify using other published work and that have theory together, that we have like at least four barrels centered at A point that we call B at beta. We have a hole, and it's not easy to know exactly if it's a hole or an electron pocket, even from calculation. Sorry, maybe you could help me that later. But near the center of the zone that we call alpha 2, and then we have a large electron pocket centered at Z that we call alpha 1, and then a small one. Sorry, I had first put gamma here, but it's Z, so I cover Z, but there is a band on the bottom here that we call delta, and that does not change much anyway. So this is all in agreement with work from those names I got from Professor Kaminsky paper on the same compound. So this is how I summarize everything very on the CeIrIn218. So those are calculations from Professor Kaminsky's group using DFT for rhodium. This is a pretty new work from a group of Professor Cutler on CeIrIn2 iridium unite. And nice thing here is that we have gamma and Z points in low and high temperature, and that what we see on experiments. So that's real life, beautiful pictures, not so beautiful ones. And low and high temperature. And well, as I told you, we are near Z, but it seems that we remain with some feature of the gamma point. Maybe V0 is not that perfect on my calculations, but that seems to me that is that part here. But also the calculations here are made for 1000K, and we are still on 300. So maybe are some features that are still here from temperature evolution. So I just show you here that we have gamma point also that fits very well. So that's why we believe we are very at Z point on 22. So then what happened when we changed temperature and see the evolution of the Fermi surface of CeIrIn2 rhodium unite? So here I'm pointing just the center of the brilliant zone. So because for not all experiments, I have the barrels that I know that play a role. Now that I saw Professor Cutler work, they kind of move in size, but it's hard to determine experimentally those corners of the brilliant zone. And I guess those new analyzers might help with that, because we don't need to move the sample anymore in front of the beam. So my guess is that we're gonna have a better resolution. But anyway, if we go from low to high temperature here, we see a nice change on those pockets around gamma, around Z point, sorry. And from like extensive studies on T-dependent ARPs, we could conclude that the main changes are happening around 200, 250K. So those big topological changes in the Fermi surface. And those results, they suggest that changes in the Fermi surface topology are associated with the fact that we are changing from gamma 7 states to a gamma 6 one. So the big change in the crystal field here is the big change we could see on the Fermi surface topology. So just pointing that we don't see change at all from basically 150 to low temperature. So, and then just almost at the end, talking about the F condition electron hybridization. So we all remember that depending on the strength of the hybridization, some bands can be affected and can show the hybridization gap. So that can be taken as like a hallmark of the heavy fermion behavior. So I will come back of those indices at Fermi level. I showed as a function of temperature, and I'm talking about that side now. So we have a big bright band here that don't move at all. And we have like a shoulder here that is moving, oops, sorry, toward higher values of K. And that we can see if I give a zoom in very, very specific experiments like circular polarization and everything. So that band here is going, is moving and shift, but the shift is very small, like at 100 milliV, it's about that size. But what I would like to point here is that I call that band here the M-shaped band. And that band never crosses the Fermi level at all as a function of temperature. And the band that crosses is the one that does not move on K, and that I colored on white here. And that one is the linear band that shows a hybridization gap. Oh, I'm telling you the result below the 20K. So talking about the gap now, hybridization gap. So we compare high temperature with low temperature, and well, from maps, I'm telling you, it's impossible to say anything. But then we took now EDCs that are energy distribution curves at KF, and so for that linear band here, and what we did, we compared that with gold at same conditions, like same energy, what is very important to determine the gap, as we are on a synchrotron, so energy, the energy that you set on your monochromator is not always the energy you get after your optics. But then we have the gold, we set exactly the energy we had, and we also got it on the same temperature. So we had the setup at Professor Campos' chamber, in which we had gold and then sample. So we measure gold, we move sample, and then we measure the sample. So it's on the same experimental situation. And here I pointed that I'm using raw data, not Fermi divided or symmetrized ones. So if we compare 60 Kelvin data from sample with gold, we see no gap. And if we compare 10K data with gold, we see a shift of the spectral function. So we can then do that a little bit to function of temperature. So that's 30K no gap, 20K we see for about, okay, 4 millieV. And if we go the lowest we could go at 5, we see 8. So you're gonna remember I told you my resolution was about 15. So yes, we are inside our resolution, but even though it's like behavior that we could follow as a function of temperature, so that's hard to quantify the size of the gap, but it's, well, I tried to show you here. So then that's the gap's a function of temperature for those points I have. And then if I play around the Brillouin zone, I don't see gap, big gap at any other places. I'm showing you here at the corner, so at the barrel zone, the corner of the Brillouin zone. And so that suggests that the 4F electrons have stronger hybridization with the conduction electrons that form the gamma and Z point, as already discussed it in Professor Kotliar paper on the 115's, that the CeIrIn is hybridizing more with the indium out of plane. So, and if we dope with cadmium, showing very fast that we see no gap at all. So it's another microscopic evidence that hybridization is being reduced when we dope with cadmium. And I'm just showing you here very fast that if we go to the other place of the Brillouin zone, so at the corner, we see no difference. At the middle of the Brillouin zone, no difference between doped and undoped sample. And then all difference is around the zone center. It's kind of shifted 100 millieV when we dope the sample. So comparing Fermi surface, of the doped compound is most likely the surface, isoenergetic surface at minus 100 millieV. So cadmium is possibly shifting the chemical potential, but that affects only the bands around the center of the Brillouin zone. That also indicates that most of the effects of the interactions between CeIrIn and indium are out of plane. So then just concluding the hybridization gap on the CeIrIn to rhodium indium 8. What is nice is that temperature decreases. We clearly see the opening of the hybridization gap at the ARPIS at around 20 K. That is 1 order of magnitude higher than coherence peak of the resistivity curve. So the hybridization is strong at around the Z point and no longer exists when we doped with cadmium. And so we would like to notice that seems that we have a propitious scenario to see the hybridization gap for CeIrIn to rhodium indium 8 because of simple explanation here that like first excited state on CeIrIn to rhodium indium 8 is about 70 K. That is from crystal field calculation and also thermal expansion measurements from Malinovsky. And that is well above the coherence temperature. And meanwhile, on the CeIrIn 115's, first excited state is around 70, reasonably close of the maximum of the resistivity, that is in that case is 50. So the higher coherence energy scale on the 115's might maybe smoothed out the spectral features to a wider and higher temperature range, so which might at the end make them difficult to be observed experimentally. And so that just last data that I included after seeing a nice presentation from Professor Dellinger for the CeIrIn cobalt-indium 5. So this is on resonance data taken at the Elena and Brazilian light source. So that's the raw data, second derivative data. So we can, that around gamma, so at 121, we are near gamma back. This is a zoom near EF, where one can see the hotspots of the FD hybridization, like like Professor Dellinger showed yesterday for CeIrIn cobalt-indium 5. So, but unfortunately, I don't have those measurements as a function of temperature. I can only show you that if we move around K, that effect is like we see bigger 5F peak near the bands that crosses the conduction bands for those spots here. And if we compare, this is just corner of the Brillouin zone where we still seeing the effects, and that finally I compare low temperature data with high temperature data where we cannot see any hybridization peak near EF, but unfortunately I don't have a temperature evolution to try to set the Kondo scaling for that compound. So strong peak near EF or low T that disappeared 200 is evidence of FD hybridization. And if we want to keep playing, and of course I don't have time to talk about that, but we can dope those compounds with tin, with gallium. Those are just what's coming next. So tin, we saw in our results that is more effective to hybridization effects, while gallium also show unexpected results on T-maximum behavior. So since that for gallium, there is bigger competition between hybridization and crystal fields effect. So I left you with my final remarks that I will come back. So those are future perspectives of other measurements that, especially the absorption, X-ray absorption experiments that should be done to to get the crystal field splittings. And thank you all. I leave you here with that. So thank you.
Okay, let's unmute yourselves and give Chris a nice round of applause. So we are running late, so maybe 2 short questions.
Maybe I can ask one.
Philip, please.
Perhaps taking a step back, I'm wondering if you could comment, since the 218s are so similar to the 115s, but yet they do have some differences. What do you see as the advantage of studying the 218s? What new information can we learn by looking at the 218s that we wouldn't get from looking at the 115s?
Well, I think a new piece of information is that we should consider all the excited states to explain the physical properties, not just what is happening on the ground state. And I would say that those ARPA's data on the 218s are, at least on the Rodion member, are easy to see the hybridization gap because of that, what I explained. Exactly because of we have less hybridization on that compound, it can make it suitable to see other effects that the broadening of the Kondo effect would not allow us to see. That one thing.
I hear it's also easier to cleave the 218s for the ARPAs.
It's easier? Oh, maybe. I never had problems actually, and they are pretty reproducible. And we never got other surface, final surface cleaving. So it seems that we always cleave on the same final surface for that.
Thanks.
Okay, thank you.
Can I ask a question, please?
Sure.
Yeah, Chris, is there any information about the nodal structure of the superconducting state known, NMR or thermal conductivity? Have these measurements been done on the superconducting states of the 218s?
Not that I know. Sorry, maybe Pascual know or Denise.
Maybe it's an experiment. People haven't got round to doing it yet. I think it'd be very interesting to know if it's a D-wave superconductor.
Yeah, well, we could use, no, we couldn't. Yeah, no ARPAs for that. Well, maybe 2K. There are some newer beamlines that we can have a helium-3 cryostat, so we maybe could try the half-half sample, but then I can tell you that those samples have lots of disorders, so I'm not so sure how good it's going to be for ARPAs, but I think it should be tried, and 2K is not that bad anymore for ARPAs.
Has NMR been done on them?
Not so far.
Oh, that would be a first step, I think.
Yeah, true. So
yeah, three angel sites, very complicated, but it should be very important to do it.
Yeah.
Okay, so any other questions? Okay, if not, let's thank Chris again.
Thank you.
And let's move. Denise, do you want to say something? Okay, so let's move to the next talk. So you'll be given by Steffen Wirth from Max-Planck Institute for Chemical Physics of Solids, Dresden, Germany. And the title of his talk is The Structure Complexity in CeIrIn5 and CeCoIn5.
Okay, thank you very much for the introduction. And also I would like to thank Philip for setting up this workshop. I would have loved to come over to Los Alamos, but so be it. Okay, and thanks to all of you for staying so late, at least here in Europe, it's already pretty late. So I would like to talk a little bit about some structural peculiarity in the 115s which may have some impact on some of the physical properties, at least at low temperatures, and that actually may have also some implications beyond the 115s. So you already see the outline of my talk here. I think I can go pretty quickly through the phase diagram because Piers gave a very nice introduction, and I'll talk about X-ray diffraction and SDM measurements we did on these compounds. So I think the motivation here is pretty straightforward. We are studying the complex physical properties that for these materials, and this of course requires some structural information down to the atomic level. But if we do that, then we are facing basically two issues. If we either go for atomically resolved probes, then we have to ask the question whether the area we are looking at is representative of the whole volume. And that's something I always have to worry about in my SDM. On the other hand, if we go for global probes, then of course you have to ask what happens locally. And so what we set out of doing here is actually a combination of methods, and we wanted to make sure that we are actually looking at the very same samples. I think only then it makes sense, yeah. Okay, so before I actually get into physics, I would like to acknowledge my collaborators. So samples came from Los Alamos. X-ray diffraction was done in-house by Yuri and Michael. SDM was done by my former student Steffen, and I had very nice discussions with Stefan Kirschner and Frank Steglich. But I should point out, actually, the main driver here is Yuri Green, with whom I had lots of discussions and really enlightening discussions about structural properties, and he has just a superb insight into these materials. Okay. Now, I think I can go very quickly here. I wanted to say a few words about the 4F materials in which you can find the Kondo and the RKKY interaction, which result in different ground states. Kondo would give you a non-magnetic ground state, RKKY would lead to a magnetic ground state. And since they have different dependencies on the coupling, you can actually play with them. And that's very nicely shown here in the phase diagram of cerium palladium to silicon 2. I think also Piers already showed that. But what you can see is you can naively drive the nail temperature here with the application of pressure to basically zero. And of course, those materials are of most interest in which we can actually have access with our experimental tools to this point here where the nail temperature would disappear. But then, as you see, superconductivity is popping up, and that's the underlying theme also for the cuprates. I really don't want to go into that too much here. Now, the generalized phase diagram, which I want to discuss a little bit here, is this as shown, as taken from the paper by Braun, where you have the magnetic order on the one side, the Fermi liquid properties on the other side, and in between you have this quantum critical funnel. And this quantum critical point then here is basically masked by superconductivity, which in many cases is unconventional, be it with respect to the pairing symmetry, a pairing mechanism, or the order parameter. And there are proposals that this is magnetically mediated in the 115s. And I just wanted to point out that the 115s helped and help answering many of these questions. Now, also the structure has been shown several times already, but that becomes crucial for my talk here. You all know the cobalt and the iridium variants are unconventional superconductors with the transition temperatures as shown here, but they are also close or near to magnetic ordering. And that has been shown by finding anisotropic spin fluctuations either on NQR or in neutron scattering measurements. And of course, the whole thing becomes much more prominent if you look at the rhodium counterpart, which is a nail antiferromagnet with a nail temperature of 3.8 Kelvin, and which gets superconducting here under pressure. And pretty soon after the discovery of superconductivity in the 115s and cerium cobalt indium 5, there was also the discussion of a field-induced quantum critical point by Andrea Bianchi or Paglioni in 2003, and I've taken here a phase diagram from Philip's paper, and that already shows that there is quite some scatter here in the data. So we thought, okay, let's do some Hall effect measurements to actually line out here the crossover from lambda Fermi liquid behavior to the non-Fermi liquid behavior. And if you look at this, then you would extrapolate to a quantum critical point here inside the superconducting dome. This is in correspondence with, let's say, seeing only part of this generalized phase diagram, and we just have the materials parameter such that this part here is not seen. Of course, there's quite an error bar involved here. So if we compare to other measurements by Philip, this would be MR measurements or thermal expansion also on, you again see that there is some scatter here, but I would say you can safely say the quantum critical point here is inside the superconducting dome. I would like to point out that Yoshito Kiwa already posted in the contributed talks or also a talk with respect to this phenomenon. So let me just give a little bit of an overview by mentioning again, we have this competition of the two energy scales. So now if we look into the cerium cobalt indium 5, we have a little bit a higher ratio of the energy scale of the RKKY under action with respect to the Kondo scale. So we see this part of the phase diagram. If we do the same scaling as we did for the Hall effect here in the cerium cobalt indium 5 for the cerium iridium indium 5, then you would actually extrapolate here to the somewhat negative field side. Of course, that's now just, you know, phenomenology. So in this case, I would draw the phase diagram as outlined here, so you just don't see the quantum critical point. The cerium rhodium indium 5 would actually also fit into this picture, but I don't want to discuss this because there are some complications that had been discussed earlier in this workshop already. Now, one other nice way of playing with the phase diagram was by putting in cadmium. That is a paper by the group of Zach Fisk from 2006. And you see with cadmium doping, you suppress the superconductivity and antiferromagnetism pops up. So we thought, okay, let's have a look at the sample here, which is at 0.75% cadmium doping, in which the energy scales of the superconductivity and the antiferromagnetism are actually pretty close to each other. So we did a number of different measurements, including neutrons, that was done by Oliver Stockert, magnetotransport, and a specific heat by Michael Niklas. So we have insight into the charge and the spin channel, also macroscopic and microscopic. And again, we made sure that we look at samples at least from the same batch. In many cases, it's actually one and the same sample. First of all, you see that the results for superconductivity and antiferromagnetism agree pretty nicely. But the point actually I want to make is here these nice neutron scattering data. As you cool down here for this particular sample, as you go below the nail temperature here, then you see the expected rise of the neutron intensity, and you can actually fit that by a Brillouin function very nicely here. But then as you go to TC, just below TC, it just stays put here. Yeah? Typically, you would expect this the intensity to go down again. And that's actually true for a number of fields here as shown here, but it's best seen in zero field. And basically, since we don't have any indication for any spatial separation in this material here, this is a second order phase transition at TC, so we think there is a coexistence of superconductivity and antiferromagnetic order. So some parts of the Fermi surface seem to be in the superconducting states, other parts in antiferromagnetically ordered states. I should also note that contrary to this general phase diagram I have shown, we don't get, even by applying high magnetic fields of 15 Tesla, we don't get into a Fermi liquid regime. We always stay in non-Fermi liquid regime. But this is just a side remark. So now let me get to the main results, the XRD studies. So the first thing we did was actually, we did all these magnetotransport measurements, and we thought, okay, let's put it also into the SDM. You know, I do a lot of SDM work. So this is just a step batch on the cerium cobalt indium 5, but what really drew our attention was this atomic resolution here on the cerium iridium indium 5 with the different arrangement here of the protrusions. I should mention here that in case of the cerium cobalt indium 5, there's very nice work here by Ali Ashtani's group at Princeton and Seamus Davis' group, and that's, however, mostly on the superconductivity. In this Nature paper, there's also a little bit of talk about heavy fermions. So let's get to the cerium cobalt indium 5. Now, typically it's assigned to the holmium cobalt gallium 5 type of pattern, as it's shown here, and it was shown many times during the workshop. So we also did some X-ray diffraction, and you see the results are pretty nice. The R value is 0.024, which is not too bad. But what was noticed is actually that the displacement parameter of the iridium was larger than the one for the cerium. That shouldn't be, because iridium is heavier, so that should be less. So that's suggestive of a lower occupation of the iridium positions. Now, and that's where Yuri, with his profound knowledge of crystal structure, comes into play. He pointed out that beside the holmium cobalt gallium 5 type of pattern, there's another type of pattern, which is called thulium arsenic palladium type pattern. And the only difference you see here is actually in the location of the iridium. Look here at the C = 1/2 plane. Here you have the iridium at the corners, and here you just shift this by along the diagonal to the center, and then you have the iridium here. So these two structures are really very similar. So there is some possibility that we have actually both structural patterns in our sample. So keeping that in mind, if you now do an X-ray diffraction experiment, you need to consider that there is no translational symmetry anymore. So we don't have any superstructure. You have to basically analyze all the symmetry-dependent reflections. And that was done. And what you get here is actually this difference electron density. So, and that's calculated from these diffraction patterns here, but only by considering the cerium and the indium atoms here. So what's basically left is the iridium. And then you see very nicely, you see the iridium here at the regular pattern. This is what we call here iridium 1 at the corner. But then there's also seems to be some iridium here at the center, corresponding to this structural pattern here. So if we keep that in mind, our X-ray experts actually designed a real new algorithm to actually look at the completeness of the diffraction data. So they did a very nice experiment here, keeping all the 1705 symmetry dependent reflections. And what you get by fitting is actually you have 98.8% of the iridium in the, let's call it regular position, but then you have this additional structure pattern with about 1.2%. If you do if you consider the symmetry independent reflection, meaning you average over the reflections, then you get something like 1.6% for this additional structural pattern. So it's pretty close to each other. So you pick your choice. So I would say something like 1.5% of this additional pattern is seen. Now, if we think about the cerium cobalt indium 5, the two of them, cerium iridium indium 5, cerium cobalt indium 5, are structurally very similar. So you could expect a similar pattern. So this was not indicated by earlier X-ray powder diffraction experiments, but when we did our elaborate experiments, then we could see that again, we found something like 1.5% of the cobalt in this case here at this additional structural pattern. I should point out so that here we have a lower contribution of the cobalt to the overall diffraction intensity, and therefore the standard deviation is a little bit higher. Nonetheless, the refinement worked stable. I should point out here that we have investigated a few samples. So I think it was 5 iridium samples, several cobalt samples, including the one I will talk about in a moment, which we used for STM. But let me make that clear here. In principle, we would have to do that for each and every sample. And I also don't want to claim that these samples are, let's say, bad also in a certain sense, yeah? I mean, these are really high quality samples. You just don't see it with a regular X-ray diffraction experiment because you actually have such a very similar pattern. These are the same atoms, yeah, just slightly displaced in the iridium or cobalt case. Now let's go to the STM. Some of you have seen my SDM. It's a low temperature SDM going to 0.3 Kelvin. But what's important is we have an in situ cleaving stage. So we cleave at about 20 Kelvin. I should point out here, I put in quite some effort with other techniques, because I think cleaving is actually a pretty high energy thing. You put in, you knock off the whole thing. You see here, this is a M1 screw glued on top of our sample here, and that's then knocked off in situ. But if you do anything else, at least I was not successful. If we did etching, annealing, sputtering, or any combination of thereof, we did see structural damage. For instance, in case of the annealing, some indium segregated out, so that's no good. So this is an overview picture of the atomically resolved iridium surface, but let me directly go into this picture here. The sample was actually mounted with the AB plane perpendicular to the tip. So we come down with the tip from the top, and the sample, the AB plane here is perpendicular to the tip. So that's this plane here. Now, along this line, this red arrow here, what we actually saw was the field of view is inclined by 37 degrees. So if you think of 37, that's quite a number. So what's actually closest by, which could give you a 37 degrees inclination, would be a 113 plane. Other planes with lower indexes are the 103 or the 102, which are a little bit off. But I'll argue that this is actually what we are seeing is the 113 plane. And now I look along this direction here, which is actually not inclined at all. So these brightest corrugations here have a distance of about 6.7 Armstrong. And if you now look at the cell here, then you see this corresponds to square root 2 of A, which is 6.6 Armstrong. So that's a pretty nice agreement. So that fits very well. Also, if you look very carefully before I switch, you see here there is some less bright corrugation. So if you zoom into here, if you take a height scan, so it's not as high, but the distances are actually the same. So we think this one here could be the iridium, this one here, the cobalt, which we are seeing. And that's supported by the fact that we are actually have applied here a positive bias voltage. So we look at the unoccupied states, and according to these band structure calculations here by Hager et al., at 0.6 volts, we actually see mostly iridium, indium hybridized bands. Now, so with this, we see the 113 plane here. Now, what does it mean for us? How does it help? So it's a pretty strange plane here in the crystal structure. But now with this, we can actually get to the bottom of these different arrangements here. If I now take a line scan here along this line, which corresponds to the triangular arrangement here, look here. So we actually see distances here, which are 13.6 angstrom apart. So this corresponds to a distance between the iridium here of 12.9. This is now the 113 plane of the holmium cobalt gallium 5 structure, and you expect this triangular arrangement. But if you have the other type of structure, then you actually, due to this displacement of the iridiums by this half-half in the 0.1/2 plane, we now expect to see a rectangular arrangement, and that's exactly what we are seeing here. And also, if you now look at the distances, that fits well. I mean, not too well, but please keep in mind, we have a steep inclination here, so we have to correct for that, and the error bar in this case is much higher than if we go here along the lines without any inclination. And I think it's actually pretty nice to have a tilted plane, a plane tilted away from the AB plane, because it can then much easier detect such different structure types. Now, of course, the question is, this is a strange plane, 113. So is this actually reasonable? And that's again where Uri Green came into place. He did an analysis of the chemical bonding via the electron localizability approach. And the idea is that the cleaving probably takes place with along a plane that keeps the strongest bonds in place. So with this bonding analysis, we should be seeing where a cleaving might happen. So this is what he got. Now here, what he found is that actually there are three preferred cleaving planes. One involves only the indium bonds. So you have here the in-plane and the out-of-plane indium here. And look at these these yellow spots. This is where most of the localization takes place. This is where the bond takes place. But this is actually best seen here, where we see the indium segment. And if you look here, within the iridium here, we have also some bonding here. And you see that this actually is the 001 plane in this case, because this is in the plane here outlined by the 4 iridiums. You don't see the one on the back. Now, so from the bonding strength analysis, it's actually preferable that, or it makes sense that for the iridium, we have the 113 plane. But I should point out here that now we actually can have 4 domains, and that's why the surfaces look so rough. In case of the cobalt, you actually have a preferred cleaving plane along 001, and I already pointed out that this has been observed very nicely. And also very recently, this is another work by the group of Ali Ashtani. Also, the 100 plane has been observed. So all these planes, which Yuri had predicted earlier, actually have now been observed. Now, of course, if you want to do here a comparison between SDM and XRD, you would like to do that on a quantitative base. But we cannot do that. We lack sufficient statistics in the SDM. We saw these patterns every once in a while, but I don't dare to actually give a number on how much of the surface we saw with this additional structural pattern. Also, I should say, we did a cleave, so we only look at the surface. So that might actually also influence what we are actually looking at. What we can say is that this additional structure pattern is only a few atomic sizes in distance, in size. So it's actually difficult to find in SDM. You really always have to zoom in. But what we would love to do is actually to compare these spectroscopy on one pattern with the other one. So to actually check on the impact of this, let's say, structural defects on the physical properties. Of course, now with the serum iridium indium-5, we are pretty close to the base temperature of our STM. That's also one reason why we also look, for instance, predominantly at the serum cobalt indium-5. But as just pointed out, in the serum cobalt indium-5, we actually never saw it in there, the 113 cleaving plane. But here I just flashed this again because Laura Green was pointing out the precursor state to superconductivity on Tuesday in her nice talk. Now, since we don't have any experimental evidence, we can turn to band structure calculation. This is again work by Gaby Kotlier's group that has been mentioned several times already. And he pointed out that the out-of-plane hybridization, meaning now the cerium is at the center, the iridium is up here, that the out-of-plane hybridization here with the indium is much stronger than the in-plane hybridization. Yes, like this one here. And already in his paper, he pointed out that this is the whole thing is very sensitive to iridium substitution up here, because these indium atoms here not only strongly coupled to the cerium, but also to the transition metal. So it is conceivable that if the transition metal moves here to the corner, note this is a different structure view as I've shown before, then one might have different hybridization. And we actually know that this is very important, what is actually located here, because if we change the transition metal, and that's the nice work by Andrea Severin and her group, we know that the properties change quite a bit. So I would argue that is actually in favor that a displaced transition metal from here to here also influences this competition. However, we have looked and we haven't seen anything so far experimentally with our STM. In fact, I should say that for the cerium iridium indium-5, we never actually saw superconductivity, but that might be due to the fact that the base temperature of our STM is so close to the superconducting transition temperature. Now, it's getting late, so let me summarize here without further ado. We have looked at the very same ceramic crystals with STM and XRD, and we found this additional structure pattern. It's only 1.5%, but it's present to the best of our knowledge throughout the whole bulk. Now, why would we worry about 1.5%? I mean, first of all, these structural defects, so I would like to call them, they can be expected whenever two closely related or more than one closely related structure types can be realized. And that's also seen, for instance, in our beloved 122 structure here. And of course, the point is, if we look at very details of the phase diagram, and sometimes we talk about 1 or 2% of the electrons, then we should keep in mind that that could be simply caused by, or at least supported by, such structural imperfections. Again, I should like to point out, I really wish to point out here, these are very clean, very excellent materials. And it's just that we looked very carefully, and only by doing so, we saw these additional structure types. And with this, I would like to thank you for your attention.
Thank you, speaker again. Thank you, Steffen, for the nice talk. So let's open the presentation for questions and comments, please. I don't see.
Wow, I cannot raise my hand.
Oh, sorry, Chris. Go ahead, please.
Hi, thank you for your very nice talk. So just like as we were discussing the 218s before, do you think that similar behavior can happen for the cerium-2 iridium indionate, and even worse, that drives it to the spin glass phase?
Yes, I really think in the related structure types related to the 115, similar things might happen. But I guess there the structural properties are even worse, I would say. This is the simplest case. So in your case, it's probably even more complicated. So I don't know whether I would dare looking at this with my STM and figuring out which atom is which one. So, but I'm almost certain if you have competing structure types that that have, let's say, a similar, that can be formed on a similar, what is it then, the enthalpy level, then you probably expect that to be present.
I think that also answers Philip's question about cleaving the sample, because I think we noticed, as I told you, I never had problem cleaving the cerium-2 iridium indionate sample, but when I tried to repeat ARPA's experiments for cerium-2 iridium indionate, I never got good like bands or band mapping. So maybe it's happening what you explained, that it cleaves where we see more density of defects.
Yes, actually, you have to be a little bit careful here. What we saw over the course of the many years is that, you know, little nuances can actually pretty much influence the cleaving behavior. I mean, I have shown you in case of the cerium cobalt indium-5, it actually cleaves pretty easily, at least along the 001. But let's say in the example of the 122 structure, for instance, we have lots of experience with the ytterbium rhodium 2 silicon 2, which cleaves nicely. But if you go for the cerium copper 2 silicon 2, very same structure, silicon based and not that much changed, yeah, it doesn't cleave at all. So we put in so much effort, also with the group of Peter Wahl, and it just, so in the end, it's nuances, and some of them just leave. And nowadays, I don't dare predicting anymore. So I would say, you know, just try, yeah, and if it works, fine, yeah.
Yeah, we saw similar with cerium copper bismuth too. It cleaves very badly, and band structure. If you have a big beam on ORPIS, it's terrible. So you have to go for micro beams and then find a good spot to see.
Yeah,
nice
I can understand that.
It's because it does not cleave. So
Yeah,
thank you.
I can appreciate that. Yeah.
I have a question.
Yeah.
Okay.
Go ahead, Hubert.
Very good talk. So I really liked it. I have two questions though. First of all, why is it that cobalt and iridium, being different in size, have the same percentage of the two phases?
Oh, well, I wouldn't put any emphasis on these numbers. I would actually argue this is just a coincidence. At least I don't have any indication, or I wouldn't know why. I think it just worked out that way for the for these materials, or for the samples we looked at. As I mentioned, I think you should, in principle, you should look at each and every sample, or at least at each and every batch here, to point that number down. But it's actually pretty cumbersome, even for the XRD. So we didn't do that. If you look carefully at the numbers, the 1.5 that was done for the cobalt with the 1001 pattern without any averaging, and if you do the same thing for the iridium, you end up with the 1.2 percentage of the impurity phase. Yeah, so there is a difference, but even, I mean, we are here looking at the limits of the XRD, so I would say all of this is within the error bar, and I really wouldn't put any emphasis on the numbers.
Thank you.
Sorry.
Thank you.
You had two questions, you said.
Yeah, the other one was, can you exclude a surface reconstruction that is actually favoring this second phase?
Well, yeah, that's actually how the whole story went. When I saw these structures, I couldn't make any sense out of it. You know, it's such a strange plane. I really couldn't make sense, so I just let it go. Yeah, and it just was Yuri who pursued it. And with the XRD, of course, he has much better insight into the bulk. I would not ever have dared publishing my results without the XRD backup. Yeah, okay. So this is just a lucky coincidence, and I really think that's the strength of these two combined methods. But again, I mean, from the SDM, it could be anything. It could be just anything. Yeah. So I really, I mean, it's how the story went. I mean, this is mostly based on the XRD results, and then going back to the SDM and scratching your head and see, okay, yes, that makes sense.
Okay, thank you.
Okay, so next question, we have a question from Joe Thompson. Joe, please.
Good morning, Steph, or good evening, I guess. Thanks a lot for a really great talk. It's a simple question. Do you know if anyone has done a band calculation on the thallium arsenic palladium 5 structure type and compared it to the holmium cobalt gallium?
No, actually, you know, when I'm not aware of it, let's put it that way. But, you know, when Philip was asking me for questions, I mean, may I pose one to the theoreticians? So maybe just look, since we lack any experimental confirmation of what's going on with respect to the physical properties, maybe do a band structure calculations. You can much more easily place the atoms where we want them than I, as an experimentalist, can do that. So no, I'm not aware of it, Joe, sorry.
Thank you very much.
Can I ask a question, Pascal?
Who's that?
Yeah.
Piers or Roman? Yeah, Piers. Okay, go ahead.
Sorry, I can't put my hand up because I'm a co-host.
Yeah, sorry, go ahead.
So I was just wondering whether these alternate iridium locations might have a connection with the unusual zero resistance region you have in the cerium iridium system. Could it be that TC for the displaced iridium phase is higher than TC for the majority phase? That would be a very crazy kind of situation if that happened, right?
Piers, thank you very much for making that clear again. I mean, that was actually my intention when I looked again on these different structure types. I couldn't see anything. But the fact that I couldn't see anything with my SDM doesn't mean there isn't anything. Yeah. Maybe I'm not sensitive enough. Maybe my surface is not good enough. Yeah. Maybe at the surface we have suppressed Kondo effect or whatever. All of this could play a role here. But I think you know, it would really be nice to do, for instance, band structure calculations. And you know, I mean, maybe I shouldn't say that. But for instance, also if you think about the two-fluid model, yeah. Maybe one way of thinking or one part that comes into play here is such as additional structural pattern. I don't know that. I have no evidence for that. But that's why I said, you know, there might be possible, you know, interpretations beyond the 115s. You know, we see these different structure types. I mean, you know the Y-bar all too well. So you know alpha and beta have very different structure types, yeah? So all of this, you know, we just don't know. And I just want to raise your attention to this fact, yeah? So if you get down to, let's say, 1% of electrons doing something in addition, so I think at least I would scratch my head and say, okay, let's have a very close look at the structure. And that's basically all I want to say. I don't have any evidence for this additional structure type actually doing something real bad. Yeah, I just don't have it.
Thank you.
Look carefully, but sorry. I think Priscilla was raising her hand.
Yeah. Okay, next question from Priscilla, please, Priscilla.
Thank you. Thank you, Steffen, for the very nice talk. So on Tuesday, we had a discussion after Katya's talk on cerium iridium medium 5 and the fact that TC there is much more sensitive to strain compared to the cobalt member. And I actually raised the possibility that the thallium arsenic palladium 5 phase could be causing this strain sensitivity. But now you tell me that even in the cobalt member, there might be the same amount percentage-wise of this minority structural pattern. So now I'm confused again, and I was just wondering if you have any thoughts on this.
Well, I mean, Priscilla, to be very fair here, you know, when I did the SDM measurements, that's some time back, and I think you guys did a superb job in also, you know, improving the sample quality even further. So if I may, I would ask you for new samples, and you know, we just look again and see. That would also answer probably a little bit more Hilbert's question, whether we are still stuck with this 1.5, or whether it has gone away, or maybe it went up or so. But it's some work, yeah. I mean, maybe that's one way of going, yeah. So as I said already, I wouldn't put too much emphasis on the 1.5. So the error bars are just, I mean, you do XRD regularly, you know the error bars. So, you know, no.
Thank you. It's very interesting and many questions still to answer.
Yeah, I know I raise more questions than I answer. I'm sorry.
We would be happy to send you samples, just so you know.
Thank you.
Okay, any further questions or comments? Okay, I don't see any further questions. So Steffen, may I ask you to stop sharing the screen, please?
Yeah. Okay.
Okay, no, so may I kindly ask audience to start the videos so we can take a nice picture of the audience for this SCES webinar and session 5 of the 115 workshop. Okay, so with that, I close the section. Maybe I give Philip, turn it back to Philip to finish this section of the workshop. Do you have an announcement to make, Philip?
Yeah, actually, I guess I just wanted to say, since we likely will lose our European colleagues for our evening session, so A, thank you for participating. B, we will be having a discussion session where hopefully we will try to identify, what are the most pressing and opportune tasks coming forward for the 115 materials in particular. So that will also be posted online. Feel free to take a look at that, send comments, and we will leave the ability to add comments open, and the videos will remain online for hopefully an extended period, months online. So if you want to check anything out afterwards, the contributed posters, contributed talks will also be available there too. So that's it.
Okay, so I think that's it. Thank you all for being here.
Thank you, everyone. It was a great session.
Later on.
Thank you. Bye.
Thank you. Bye.
Bye-bye.